The way Starbucks coffee is produced in factories is the furthest from simple possible. Each step in the creation of their coffee is crucial, with one misstep meaning an entire batch could taste horrible when you place an order. Today, we're uncovering how Starbucks coffee, Lipton iced tea, and Tim Hortons donuts are made in factories, revealing their hidden process that they need to stay on top. Starbucks coffee begins revealing its character the moment green coffee beans tumble into a roaring drum roaster, because everything that follows depends on how those pale, dense seeds respond to heat over the next several minutes. The beans enter the roasting drum in a steady cascade, sounding more like small stones than something destined to become coffee. At first, they are cool, hard, and slightly green with very little aroma. As the drum rotates, every bean rolls continuously through streams of carefully controlled hot air, while the metal shell keeps them moving in constant circulation. The temperature climbs steadily, and moisture locked deep inside each bean begins escaping as steam. The color shifts almost unnoticed from pale green to yellow, then to light tan. This is only the beginning. The real transformation is still hidden inside the beans, and over the next several minutes, they will expand, crack, darken, and generate hundreds of aromatic compounds that did not exist when they first entered the machine. As heating continues, pressure builds inside every bean. Water trapped within the cellular structure converts to steam, while natural sugars and amino acids begin reacting with one another through complex browning reactions. The beans swell noticeably as internal gases expand. Suddenly, a wave of sharp popping sounds echoes through the roasting drum. This first crack signals that internal pressure has fractured the bean structure, allowing moisture and gases to escape. The beans become lighter, more brittle, and significantly larger than when they entered. Although they now resemble roasted coffee, the roasting process is far from complete. Every additional second inside the drum continues reshaping flavor, aroma, color, and texture. The roast master, or automated roasting system, continuously monitors bean temperature, airflow, drum speed, and roast development. Hot air flows evenly through the rotating mass, ensuring every bean experiences similar conditions. Too little development leaves grassy or underdeveloped flavors. Too much heat risks burning delicate compounds before the desired profile is reached. Every adjustment happens gradually because thousands of beans must roast together with remarkable consistency. The changing aroma inside the roasting chamber becomes richer with every rotation as sugars caramelize, organic acids transform, and volatile aromatic compounds multiply throughout the batch. When the target roast profile is achieved, the entire batch empties rapidly into a cooling tray. Large paddles immediately begin sweeping through the beans, while powerful fans pull cool air upward from beneath a perforated floor. Cooling must happen quickly. Even after leaving the roasting drum, the beans still contain enough heat to continue roasting internally. Rapid cooling locks the roast level in place and prevents unwanted overdevelopment. The constant movement also keeps every bean exposed evenly to the cooling airflow, stopping the roasting process within minutes. Only after cooling does another important stage begin. Freshly roasted coffee contains large amounts of carbon dioxide generated during roasting. Rather than packaging immediately, the beans often enter holding bins where they rest for controlled degassing. During this period, carbon dioxide slowly escapes from inside the bean structure. Too much trapped gas could interfere with grinding, extraction, or package stability later. The beans continue releasing gas while preserving the aromatic compounds created during roasting, quietly preparing for the next transformation. Before any grinding takes place, the roasted beans move through extensive inspection systems. Vibrating conveyors spread them into thin layers, while optical cameras scan color, size, and overall appearance. Air separators remove lightweight fragments and loose chaff produced during roasting. Magnets capture any stray metallic particles before the beans continue forward. Every stage protects the consistency of the finished coffee while ensuring only properly roasted beans. Advanced to processing. Some Starbucks products are packaged as whole beans, but ground coffee follows another path entirely. The roasted beans travel toward industrial grinders equipped with precision-engineered rollers. Unlike household grinders, these machines reduce the beans gradually through multiple stages. The first rollers crack the beans into coarse pieces. Additional rollers continue reducing particle size until the grind matches the intended brewing method. Every adjustment changes extraction behavior later. A finer grind exposes more surface area to water, while a coarser grind slows extraction. Particle size distribution is monitored continuously because even small variations can alter the finished beverage. The freshly ground coffee moves through enclosed transfer systems designed to minimize unnecessary exposure to oxygen. Grinding dramatically increases surface area, making the coffee more vulnerable to aroma loss if left exposed. Conveyors, sealed hoppers, and enclosed augers transport the grounds efficiently while preserving as much freshness as possible. Depending on the final product, the grounds may proceed directly toward packaging or continue into extraction for ready-to-drink beverages. For bottled Starbucks coffee drinks, extraction begins inside large stainless steel brewing vessels. Precisely weighed coffee grounds enter brewing chambers where carefully controlled water begins flowing through the coffee bed. Temperature, contact time, pressure, and flow rate all influence how soluble compounds dissolve into the brewing water. As hot water travels through the grounds, it extracts oils, sugars, acids, aromatic compounds, and dissolved solids that create the recognizable coffee flavor. The liquid leaving the brewer is no longer water. It has become concentrated brewed coffee. The brewing process is carefully balanced. If water passes too quickly, desirable compounds remain trapped inside the grounds, producing a weak extract. If extraction continues too long, harsher compounds begin dissolving, creating bitterness that overwhelms the finished beverage. Automated controls continuously monitor flow rates and brewing parameters to maintain consistency from batch to batch. After extraction, the brewed coffee separates from the spent grounds through filtration systems. Fine screens and filters remove remaining particles while allowing the coffee extract to continue flowing into insulated holding tanks. The used grounds leave the brewing equipment through separate discharge systems, while the clarified coffee continues deeper into production. Now another transformation begins. Depending on the product, ingredients such as milk, cream, sugar, or flavor components are prepared separately before blending. Milk enters refrigerated storage tanks and may undergo additional standardization to achieve the desired fat content. Sweeteners dissolve into controlled syrup systems. Flavor ingredients are measured through precision dosing equipment. Each component waits independently until blending begins. Inside large blending tanks, brewed coffee combines with these prepared ingredients according to the intended formulation. Agitators circulate the mixture continuously, ensuring every portion becomes completely uniform. The dark coffee gradually changes as lighter dairy ingredients disperse throughout the liquid, creating smooth, consistent color and body. Every addition is monitored by automated flow meters and weighing systems to maintain exact proportions throughout the batch. Before packaging, many ready-to-drink coffee products undergo pasteurization or ultra-high temperature processing. Plate or tubular heat exchangers rapidly raise the beverage to carefully controlled temperatures before cooling it again just as quickly. This thermal treatment improves product stability while preserving as much of the coffee character as possible. Temperature sensors monitor the beverage continuously, ensuring every portion receives the required treatment before moving forward. The finished coffee beverage enters insulated holding tanks equipped with slow-speed agitators. Gentle circulation prevents separation, while minimizing unnecessary air incorporation. Level sensors monitor available volume, automatically supplying the filling lines as production continues. Meanwhile, empty bottles begin their own journey. Plastic bottles often start as PET preforms, compact plastic tubes already containing the finished neck and threaded opening. Infrared heaters soften the body section while keeping the neck cool. Stretch blow molding machines then pull and inflate each preform inside precision molds, forming the familiar bottle shape within seconds. Every bottle exits lightweight, yet strong enough to withstand filling and transportation. Glass bottles arrive already formed and move through inspection systems before entering internal rinses. Powerful, filtered air or sterile water removes any loose particles. Every container proceeds toward the filling line clean and ready. Lipton iced tea takes its first recognizable form when a stream of freshly brewed tea flows out of enormous extraction vessels, carrying thousands of dissolved flavor compounds that only minutes earlier were locked inside dry tea leaves. At that moment, the liquid already has its deep amber color and unmistakable aroma, but it is still only one part of a much larger process. Before this tea can become the finished drink found on store shelves, it must be blended, refined, cooled, packaged, and protected with remarkable precision. The brewing stage may look like the climax, yet it is only the opening chapter. The next transformations happen almost invisibly inside a network of stainless steel tanks, insulated pipelines, and high-speed filling equipment, where every second and every degree of temperature influences the final beverage. The tea leaves begin their journey long before brewing ever starts. Large deliveries arrive at the processing facility and are transferred into enclosed storage systems designed to keep moisture and contaminants away from the raw ingredient. Before the leaves enter production, automated sampling systems verify their physical characteristics, while vibrating screens remove dust, stems, and oversized particles. Magnets capture any stray metallic fragments that could have entered during transportation. The cleaned leaves move through enclosed conveyors toward precisely controlled weighing stations. Every batch must begin with the exact amount of tea, because even small variations influence extraction strength later in the process. Once the required quantity is measured, the leaves travel toward the brewing room, where massive extraction vessels are already being prepared. Meanwhile, treated water begins its own entirely separate journey through the factory. Since water makes up the overwhelming majority of the finished drink, consistency starts here. Incoming water passes through multiple stages of purification, including coarse filtration, activated carbon treatment, and fine polishing systems that remove unwanted tastes, odors, and microscopic particles. Depending on the facility, mineral content may also be carefully adjusted to create a stable brewing base. The treated water collects inside insulated storage tanks until production calls for the next batch. Powerful pumps then send it through plate heat exchangers, where its temperature rises rapidly before entering the extraction vessels. At this point, two completely separate ingredients, carefully prepared water and measured tea leaves, are finally ready to meet. Inside the extraction tanks, hot water begins flowing evenly through the tea leaves. Agitation systems circulate the liquid gently, allowing water to contact every portion of the leaves without damaging them excessively. Heat unlocks thousands of naturally occurring compounds, including color pigments, aromatic molecules, tannins, and soluble flavor components. Gradually, the clear water darkens into a rich amber infusion as extraction continues. Sensors continuously monitor brewing temperature, contact time, and circulation speed, because every adjustment changes the final flavor profile. If brewing stops too early, valuable compounds remain trapped inside the leaves. If it continues too long, stronger tannins begin dominating the extract. The process must stop at precisely the right moment to capture the desired balance before the tea changes character. Once brewing reaches its target, the liquid begins separating from the leaves. Stainless steel screens hold back the spent tea, while the freshly brewed extract flows into enclosed transfer lines. Additional filtration removes smaller leaf particles, creating a smooth liquid while preserving the dissolved flavor compounds developed during extraction. The tea now carries its recognizable aroma and color, but it remains far stronger than the finished beverage. This concentrated extract serves as the foundation for everything that follows. Hidden behind the walls of the blending room, the next stage quietly determines how every bottle will taste. Large blending tanks wait nearby, already connected to treated water lines, sweetener systems, and ingredient dosing equipment. Before the brewed tea enters, sweetener preparation has already begun. If granulated sugar is used, automated feeders deliver carefully measured quantities into heated mixing tanks where powerful agitators dissolve every crystal into a perfectly clear syrup. In facilities using liquid sweeteners, insulated pipelines transfer the ingredient directly into the blending system, while electronic flow meters monitor every addition. Regardless of the sweetener source, the objective remains identical: produce a completely uniform liquid capable of blending instantly with the tea extract. The syrup is filtered before leaving the preparation area, ensuring no undissolved particles continue downstream. Now the brewing room and syrup room finally connect. Concentrated tea flows into the blending vessel while sweetener enters through separate dosing lines. Treated water follows immediately afterward, reducing the concentrated tea to its intended drinking strength. Agitators circulate the growing batch continuously, eliminating concentration differences throughout the tank. Depending on the specific Lipton iced tea variety, fruit juice concentrates, natural flavors, citrus components, or additional ingredients may enter through precision metering systems. Every ingredient joins the circulating liquid gradually, disappearing almost immediately into the constantly moving mixture. From above, the blending tank appears calm, but beneath the surface, every rotation of the agitator creates complete uniformity. The beverage now resembles the finished product remarkably closely, yet another critical transformation still lies ahead before packaging can even begin. Before filling, the tea beverage usually undergoes thermal processing designed to stabilize the product while preserving as much flavor as possible. The liquid travels through enclosed stainless steel plate heat exchangers, where thin metal plates separate the beverage from heating and cooling media. Heat transfers rapidly across the plates, raising the beverage to carefully controlled temperatures for only the required amount of time. Immediately afterward, another section of the exchanger cools the beverage again. The rapid heating and cooling sequence protects product quality while preparing the beverage for packaging. Sensors monitor temperature continuously, and automated valves divert product instantly if processing conditions fall outside specification. Although this stage occupies only a short section of the production line, it plays an essential role in preparing the beverage for its journey beyond the factory. After thermal treatment, the tea flows into insulated holding tanks equipped with slow-moving agitators. Unlike the vigorous mixing performed earlier, these paddles rotate gently, keeping ingredients evenly distributed without introducing unnecessary air. Dissolved oxygen can gradually influence flavor stability, so every transfer throughout the factory is designed to minimize turbulence wherever possible. Level sensors monitor every storage tank, while automated control systems continuously balance supply between production batches and multiple filling lines operating simultaneously. The beverage now waits only briefly before the fastest machines in the factory take over. At the opposite end of the production hall, empty containers begin their own, carefully synchronized journey. Plastic bottles commonly start as PET preforms, compact plastic tubes already containing the finished threaded neck, but lacking the familiar bottle shape. The preforms enter infrared heating ovens where they rotate continuously beneath carefully arranged heating elements. Only the body softens while the neck remains cool and dimensionally stable. Once heated, each preform enters a stretch blow molding machine where a stretch rod pulls downward through its center as high-pressure compressed air expands the softened plastic outward against chilled mold walls. Within seconds, every contour appears: the shoulder, base, sidewalls, grip panels, and label surface. The bottle exits lightweight yet remarkably strong, immediately joining high-speed air conveyors that transport it toward the filling room. Before filling begins, every bottle passes through an internal cleaning station. Bottles invert, while filtered air removes any particles that may have entered during handling. They rotate upright again and move directly toward the rotary filler. At the same time, chilled Lipton iced tea leaves the holding tanks through sanitary stainless steel pipelines and approaches the filling bowl from an entirely separate direction. Two production streams that have remained independent until now finally meet. The rotary filling machine operates with remarkable synchronization. Empty bottles enter continuously through star wheels that position each container beneath an individual filling valve. As the carousel rotates, valves open precisely when each bottle reaches the correct position. The amber-colored tea flows smoothly into the waiting container, while electronic controls monitor the fill level continuously. Every bottle receives nearly identical volume despite the tremendous production speed. Once the programmed level is reached, the valve closes instantly before the next bottle arrives beneath it. The entire sequence repeats thousands of times every hour with barely noticeable variation. Filled bottles move immediately into the capping turret. Plastic closures arrive from vibrating sorting bowls that orient every cap correctly before feeding spinning capping heads. Each head applies carefully controlled torque, tightening the cap enough to create a secure seal while avoiding thread damage. Within only a few seconds of leaving the filler, every bottle is completely closed and protected from the outside environment. Now another important checkpoint begins. Vision inspection systems examine every bottle without slowing production. Cameras verify fill height, cap position, bottle shape, closure integrity, tamper bands, and overall appearance. Check weighers confirm product quantity, while automated reject mechanisms remove any bottle that falls outside specification. Every accepted bottle continues toward labeling, where another series of precisely synchronized machines prepares the product for retail shelves. Printed label film unwinds continuously from large reels, while electronic registration sensors monitor alignment marks. Rotary knives cut individual labels before adhesive secures the leading edge against each bottle. As the bottle spins, the remaining label wraps smoothly around the surface before pressure rollers eliminate wrinkles and air pockets. Some packaging formats instead receive shrink sleeves that slide over the bottle before passing through heated tunnels, where the printed film contracts tightly around every contour. Coding systems immediately apply production information, including batch identification and manufacturing details, before cameras verify that every printed code remains readable. The production line now begins, transforming individual bottles into retail-ready multi-packs. Guide rails divide the continuous bottle flow into multiple lanes, while timing screws establish exact spacing. Automated grouping systems assemble bottles into 6-packs, 8-packs, or larger retail configurations depending on production requirements. Shrink film wraps around grouped bottles before entering heated tunnels, where controlled heat causes the film to contract tightly around every container, creating compact and stable bundles. Other product formats enter paperboard cartoning systems, where flat carton blanks open automatically before bottles slide neatly inside. Folding mechanisms close the cartons, while hot melt adhesive secures every seam. Tim Hortons donuts reveal their unmistakable shape the instant a soft ring of dough drops onto a moving conveyor. But that perfect circle is only the beginning of a much longer transformation. At first glance, it looks complete, already resembling the finished donut. Yet, it is still nothing more than cool, unbaked dough with no crust, no airy interior, and none of the glossy coatings that will eventually define the finished product. As the conveyor carries each freshly formed piece deeper into the bakery, every stage ahead builds upon the last. The next few minutes will stretch the dough, fill it with thousands of microscopic air pockets, bake it into a delicate structure, and finally coat it in layers of glaze, icing, or toppings. Every machine waits for the previous one to finish its work, creating a seamless chain of transformations where even a slight change in timing affects everything that follows. Long before the first donut reaches the forming line, ingredients have already begun their own carefully coordinated journey. Flour arrives in bulk and moves pneumatically into towering storage silos where it remains dry and protected until production begins. Metering systems deliver precise quantities into industrial mixers, while separate ingredient feeders prepare sugar, salt, yeast, milk solids, shortening, emulsifiers, and carefully measured water. Every ingredient enters according to a programmed sequence because dough development depends not only on the recipe, but also on the order in which each component is introduced. Powerful spiral mixing arms rotate through the bowl, while the dough gradually transforms from loose, dry particles into one continuous elastic mass. At first, it appears rough and uneven, but with every revolution, the gluten network strengthens, allowing the dough to stretch while trapping the gases that will later create its light interior. Once mixing reaches the desired level of development, the dough leaves the mixer in large portions and travels toward resting equipment. Although nothing dramatic appears to happen during this stage, the dough is quietly preparing itself for the mechanical work ahead. Resting allows the gluten structure to relax after intensive mixing, making the dough easier to shape without excessive shrinking or tearing. Temperature remains tightly controlled because warmer dough behaves very differently from cooler dough. Sensors continuously monitor both dough temperature and resting duration before conveyors automatically release each batch toward the forming line. The dough now has the strength to hold its shape while remaining soft enough for precise forming. The forming equipment begins by feeding the rested dough through sets of sheeting rollers. Each roller gradually reduces thickness without crushing the internal structure. The dough becomes a smooth, continuous sheet moving steadily across wide conveyor belts. Thickness must remain remarkably uniform because even slight variations would produce donuts that bake differently. Optical sensors monitor the sheet while automated adjustments compensate for any inconsistencies before the dough reaches the cutting station. Now comes one of the fastest transformations in the entire bakery. Rotary cutters descend rhythmically onto the moving sheet, stamping out perfectly shaped donut rings with astonishing speed. Circular cutters remove both the outer edge and the center hole simultaneously, producing hundreds of identical pieces every minute. The remaining scrap dough surrounding the cut shapes does not go to waste. Conveyors carry it away to be blended carefully with fresh dough in controlled proportions before entering production again. The newly cut rings continue forward untouched, maintaining smooth edges that will later expand evenly during baking. At this point, the donuts still appear dense and flat. Their greatest transformation has yet to happen. Conveyors transport the freshly cut rings into a large proofing chamber where carefully controlled warmth and humidity awaken the yeast. Inside this enclosed environment, countless tiny bubbles of carbon dioxide begin expanding throughout the dough. The rings slowly increase in height while becoming noticeably softer and lighter. The surface remains smooth because humid air prevents premature drying. Every minute inside the proofer builds the internal structure that will later support the finished donut. Too little proofing leaves the crumb compact, while too much causes the delicate structure to weaken. Timing therefore becomes just as important as every ingredient measured at the beginning of production. As the proofed donuts leave the chamber, they hardly resemble the dense rings that entered only a short time earlier. Their volume has increased dramatically, and their surfaces now feel delicate enough that every conveyor transition must support them gently. Yet, despite their impressive rise, another transformation still lies ahead, one that permanently fixes their structure and creates the familiar golden crust. Instead of entering a fryer, many large-scale Tim Hortons production facilities prepare donuts through controlled baking systems before finishing. The proofed rings travel into long tunnel ovens, where multiple heating zones surround the dough with carefully regulated temperatures. Heat first begins setting the outer surface while the interior continues expanding. Water trapped inside the dough converts to steam, stretching the already enlarged air cells created during proofing. Proteins strengthen into a permanent network while starches gelatinize, giving the donut its soft but resilient crumb. As the conveyor advances through each heating zone, the pale dough gradually changes color, developing a light golden exterior while maintaining a moist interior. The exit from the oven introduces another critical stage that receives far less attention than mixing or baking, but is equally important. Freshly baked donuts contain considerable internal heat. If they moved immediately into icing or glazing, excess warmth would thin the coatings and prevent proper adhesion. Cooling conveyors therefore stretch across long sections of the bakery, allowing air to circulate gently around every donut. During this journey, the crumb stabilizes, the crust firms slightly, and excess moisture redistributes throughout the interior. By the time the donuts reach the finishing area, they have cooled enough to receive decorative coatings without compromising texture. Now the bakery begins creating the enormous variety associated with Tim Hortons donuts. Plain donuts branch toward packaging almost immediately, but many others enter glazing systems, where warm glaze continuously circulates through shallow reservoirs. As each donut passes beneath the glazing curtain, its upper surface becomes coated with a thin, glossy layer. Excess glaze drains away, while the remaining coating gradually sets into a smooth, slightly translucent finish. The process lasts only seconds, yet it completely changes the appearance of the product. Corny chocolate production begins with a hot binder syrup forming inside a heated mixing vessel. Sugar syrup, glucose syrup, honey-like syrup components, fat, cocoa ingredients, and flavoring are measured into the tank. The liquid warms as the agitator turns. At first, the mixture is thin and separate in places. As heat spreads through the vessel, the sugars dissolve, the fat disperses, and the binder becomes glossy and uniform. This binder is the part that turns loose grains into a bar. It must be sticky enough to hold cereal pieces together, but not so fluid that it runs away from the mixture. It also must cool into a chewy, stable structure. The tank controls temperature and mixing speed so the syrup stays pumpable without becoming too dark or too thick. Dry cereal ingredients are prepared on a separate line. Rolled oats, crisped rice, wheat flakes, corn flakes, puffed grains, and small cereal clusters can be combined depending on the specific bar formula. Each ingredient moves through its own feeder before joining the main dry blend. The dry ingredients pass through screens before mixing. Oversized clumps are removed. Fine dust and broken fragments can be reduced so the bar does not become powdery. The goal is a mixture with visible grain pieces and enough small particles to fill spaces between larger flakes. Chocolate chips or cocoa-flavored pieces may be added to the dry stream. These pieces must be cool and firm before they enter the mix. If they are too warm, they smear into the cereal instead of remaining as separate inclusions. The feeding system meters them gently so they do not break apart before forming. The cereal blend enters a large horizontal mixer. The paddles rotate slowly, lifting and folding the light grains without crushing them. The hot binder syrup is pumped in through several nozzles, spreading across the moving bed of cereal. The syrup lands as thin ribbons. The mixer turns the grains through the syrup again and again. Dry flakes become glossy. Puffed pieces catch the binder in their rough surfaces. Small grains settle into gaps between larger pieces. The mixture changes from loose cereal into a sticky, connected mass. The timing of this stage is critical. Too little mixing leaves dry pockets that fall apart later. Too much mixing breaks flakes and compresses the texture. The mixer must coat the grains evenly while preserving their shapes. Once the cereal mass reaches the right consistency, it discharges onto a forming conveyor. The mixture is warm, sticky, and uneven at first. It drops as a thick layer and passes beneath spreading rollers. Side guides contain the edges so the layer stays at the correct width. The forming section compresses the mass into a continuous slab. A first roller spreads it. A second roller levels it. A calibrated compression belt presses from above, while the conveyor supports it from below. The grains lock together as the binder fills the spaces between them. The slab thickness determines the final bar height. If the slab is too thin, the bar becomes brittle and flat. If it is too thick, the center may not cool evenly. The forming equipment holds the layer at a steady height across the entire width. The top surface is textured by the grains, but the slab must still be even enough for cutting and coating. The rollers do not grind the cereal smooth. They press it just enough to bind the structure while leaving visible oat flakes, puffed grains, and crisp pieces. The warm slab moves into a cooling tunnel. Cold air passes over the top and through the conveyor area. The binder begins to firm. The mass changes from soft and sticky to flexible and stable. It must cool enough to cut cleanly without cracking. Inside the slab, the syrup sets around the grains. Each piece becomes part of a larger network. The bar texture depends on this balance. The binder stays chewy, while the cereal pieces remain crisp or lightly crunchy. After cooling, the slab reaches the cutting section. Long circular knives slice it lengthwise into continuous strips. The blades pass through grains and binder, leaving straight edges. The strips separate slightly as they move forward. A cross cutter then divides the strips into individual bar lengths. The blade moves in rhythm with the conveyor. Each downward cut creates another bar. The cut must be fast and clean, because slow pressure would drag the sticky binder and deform the edge. The separated bars now have their cereal structure, but the chocolate part still needs to be added. Chocolate coating is prepared in a separate system. Cocoa ingredients, sugar, milk powder, cocoa butter, or coating fats, and flavor components are mixed into a smooth chocolate mass. The mixture passes through refining equipment to reduce particle size and remove grittiness. The chocolate then moves through conching or intensive mixing. The mass becomes smoother and more fluid. Fat coats the dry particles. The chocolate develops the flow needed for coating the bar evenly. Before coating, the chocolate is tempered or conditioned depending on the coating type. Temperature is adjusted so the chocolate sets with the correct firmness and surface finish. The coating must remain liquid at the enrober but become solid quickly after cooling. Corny chocolate bars can be coated in several ways. Some versions receive chocolate on the bottom only. Others are dipped, striped, or fully enrobed. For a bottom-coated bar, the cereal bar travels across a chocolate bed or roller that applies a layer to the underside. The underside touches the liquid chocolate and picks up a smooth base layer. Excess coating is scraped or controlled by rollers so the layer is even. The chocolate base helps hold crumbs, adds flavor, and creates a clean surface against the wrapper. For a fully coated format, the bars enter an enrober. They ride on a wire mesh belt under a falling curtain of chocolate. The chocolate flows over the top, down the sides, and around the cut edges. A lower coating stream covers the underside through the mesh. Excess chocolate drains away and returns to the circulation tank. Air blowers remove extra coating from the top and sides. The airflow smooths the surface and controls thickness. The coating must cover the uneven cereal edges without becoming too heavy. For striped bars, the main chocolate layer sets slightly before thin nozzles apply lines across the top. The nozzles move, or the bars pass beneath them at a controlled speed, creating repeated chocolate stripes. These lines sit on the surface as a decorative and flavor layer. After coating, the bars enter a cooling tunnel. Chilled air flows around them while they move forward. The chocolate changes from liquid to solid. The surface firms first, then the full coating stabilizes. The cereal center remains intact inside the shell or beneath the base layer. Cooling must be gentle enough to avoid cracking, but strong enough to set the chocolate before wrapping. If the coating is still soft, it will smear on belts and film. If it is cooled too aggressively, the surface can lose its smooth finish. At the tunnel exit, the bars pass through inspection. Cameras check length, width, coating coverage, broken edges, exposed cereal patches, chocolate smears, and missing stripes. Metal detectors scan the product stream. Bars outside the programmed limits are rejected automatically. Accepted bars move into the wrapping section. Timing belts separate them into equal gaps. The bars align lengthwise, so each one enters the wrapper in the correct position. Printed film unwinds from a roll. Tension rollers keep the film smooth. Registration sensors read printed marks so the wrapper design lines up with the bar. The film folds around the product through a forming box. A longitudinal seal closes along the underside or back of the wrapper. Heated sealing wheels press the film layers together. Cross-seal jaws close the front and back ends of each pack, sealing and cutting one wrapped bar from the continuous film. The wrapper protects the cereal texture from moisture and keeps the chocolate surface clean. It must sit close to the bar without crushing the grains or marking the coating. Wrapped bars pass through check weighers. A short bar, broken bar, or missing product produces a weight outside the target range. Vision systems inspect seal quality, film position, print alignment, and code placement. Defective packs are diverted from the line. Skittles centers are cut from a thick, fruit-flavored candy rope before their colored shells are built around them. The center mass starts as a chewy sugar base. Sugar, glucose syrup, and water are cooked together until the mixture reaches the correct solids level. Heat drives away moisture, and the syrup becomes dense, clear, and heavy. The cooked syrup is not yet a finished candy. It is a hot, elastic base that needs acid, flavor, color preparation, cooling, and forming. The hot candy mass moves onto a cooling table or through a continuous cooling system. As it cools, it becomes thicker and more workable. Acid ingredients and fruit flavor components are added while the mass is still soft enough to fold. The mixing action pulls the flavor through the candy until every section has the same sharp fruit profile. The base must stay pliable. If it cools too far, it becomes difficult to shape. If it stays too warm, it stretches too much and will not cut cleanly. Temperature controls the entire forming stage. The candy mass is worked into a long rope. Rollers and forming wheels pull it forward and reduce its diameter. The rope becomes smooth, rounded, and even. Inside, the candy is dense and chewy. Outside, the surface firms just enough to hold shape. The rope enters a cutting machine. Rotating knives or forming dies divide it into small pillow-shaped centers. Each cut creates a soft pellet with rounded edges. The pieces are still not shiny, hard, or fully colored like finished Skittles. They are chewy cores waiting for shell coating. The cut centers move on to cooling conveyors. Air removes heat and firms the surface. The centers must become strong enough to tumble in coating pans without sticking together or deforming. They remain chewy inside, but the outside develops enough firmness for panning. The centers pass through sizing screens. Pieces that are too small fall away. Oversized pieces and doubles are removed. Correct size centers continue toward the coating area. The sorting step helps the finished candy feel consistent, even though millions of pieces move through the line. The accepted centers enter large rotating coating pans. These pans are wide, smooth, and tilted. As each pan turns, the centers climb the inner wall, then roll back down over one another. This tumbling motion exposes every surface repeatedly. A sugar syrup is prepared separately for shell building. Sugar, glucose syrup, water, color, and other coating ingredients are cooked and held at a controlled temperature. The syrup must flow through spray nozzles, but it must also dry into a hard shell once applied. The first shell layers are usually built gradually. A small amount of syrup is added to the tumbling centers. The syrup spreads across the surface. Drying air flows into the pan and removes moisture. The thin layer hardens. Then another small amount is added. The shell forms through repetition. Spray, tumble, dry. Spray, tumble, dry. Each cycle adds a little thickness. The pieces become stronger and smoother with each pass. The centers stay chewy while the outside begins developing a crisp sugar shell. The pan speed must be carefully controlled. Slow tumbling can cause clumping and flat spots. Fast tumbling can chip the growing shells. The best motion keeps the pieces rolling continuously, with a dry rattling sound as the shell hardens. Drying air is adjusted for temperature and humidity. If the air dries the syrup too slowly, pieces stick together. If it dries too fast, the surface can become rough. The coating layer must spread before it sets, then crystallize evenly. Each flavor color batch is handled separately. Lemon pieces receive yellow coating. Orange pieces receive orange coating. Strawberry, grape, lime, green apple, or other flavors receive their own colors depending on the product version. The fruit center and outer color must match the intended final mix. As the coating builds, the pieces change from soft pellets into bright candy buttons. They become smoother and rounder, but they keep a slight flattened oval shape. The shell grows thick enough to give the first crisp bite before the chewy center begins. After the main color coating is finished, polishing begins. A very small amount of polishing solution is added while the candy continues tumbling. Friction between pieces smooths the surface. The candies become glossier. The shell shifts from dull color to bright shine. The polished Skittles leave the coating pans and move onto cooling and drying conveyors. The shell must stabilize before printing. If the surface remains tacky, the printed mark can smear. If the shell is too brittle or dusty, the print will not transfer cleanly. The pieces pass through screens and air separators. Loose sugar dust, broken fragments, and clusters are removed. The accepted candies move into color-specific holding bins. Each bin holds one finished color and flavor. The white S is applied in a printing stage. Candies feed from hoppers into channels or pockets that position them for contact with printing equipment. A food-grade white marking material transfers onto the shell surface. The equipment touches each candy briefly, leaving the letter without cracking the shell. Printing small rounded candies is difficult because each piece can land at a different angle. The feeding system uses vibration, channels, and controlled flow to improve orientation. Not every motion is forceful. The candy must move fast, but the shell surface must remain intact. After printing, the candies pass through a short drying section. Air sets the printed mark so it does not smear during blending. The pieces now have the full outside appearance: bright shell, glossy surface, and white printed letter. Blending happens after colors are finished and printed. Each color feeds from its own hopper. Vibrating feeders release measured amounts onto a common conveyor or into a blending drum. The system controls the ratio, so the finished bag receives the intended color mix. The blending motion must be gentle. Skittles shells are hard, but they can chip if dropped from high distances or squeezed under heavy pressure. Chutes are curved. Conveyors are controlled. The candy flows like small polished stones without being crushed. The mixed candy moves toward the weighing system. A multi-head weigher handles the irregular flow. Candy feeds into many small buckets. Each bucket holds a partial amount. The machine calculates which combination of buckets equals the target pack weight. The selected buckets open together. Skittles drop into a funnel and enter the bagging machine. The fall is short and guided to prevent cracking or bouncing out of the forming tube. Packaging film unwinds from a roll. The film is printed before it reaches the machine. Registration sensors read marks on the film, so each bag is cut and sealed in the correct place. The film passes over a forming collar and wraps into a vertical tube. A vertical seal closes the back of the tube. Horizontal jaws close the bottom. The weighed candy drops into the open package. The jaws close again above the candy, forming the top seal of one bag and the bottom seal of the next. A knife cuts between seals, releasing a finished bag. The sealed bag contains a controlled amount of mixed color Skittles with enough internal space to move without crushing. The film protects the candy from moisture because humidity can dull the shell and make the surface sticky. Pepsi cans lock shut under a double seaming head while the cola inside is still cold, pressurized, and fizzing against the lid. A filled aluminum can enters the seamer through a star wheel. The can body is open at the top, and the carbonated Pepsi sits just below the rim with a controlled headspace above it. A lid drops onto the can flange. The seaming chuck holds it in place. Rollers move in with precise pressure, curling the lid edge and can flange together into a tight double seam. The first roller forms the metal. The second roller compresses it. The seam becomes a folded mechanical lock that holds carbonation without glue. The can leaves the seamer sealed, rigid, and ready for inspection. Inside, dissolved carbon dioxide remains trapped under pressure. Before the can reaches the seamer, it is filled in a rotary pressure filler. Empty cans move into the filler after rinsing. They are spaced by star wheels and carried around a circular filling bowl. Each can rises under a valve. The valve controls liquid flow so the carbonated drink enters quickly without excessive foam. The Pepsi stream is cold at this point. Cold liquid holds carbon dioxide more efficiently and behaves more calmly during filling. The dark cola enters the can in a controlled flow. The level rises with fine bubbles moving upward through the liquid. When the programmed fill height is reached, the valve closes and the can moves immediately toward the lid feeder. The filler must work with speed and restraint at the same time. Carbonated liquid wants to release gas when pressure changes. The filling valve shapes the flow to reduce splashing. The short transfer from filler to seamer prevents gas loss before closure. The carbonated beverage arrives at the filler through closed stainless steel pipework. The line remains pressurized and smooth. Sharp turns and sudden pressure drops are avoided. The liquid moves from the carbonator to the filling bowl without open exposure. Inside the carbonator, chilled flat Pepsi receives carbon dioxide. The liquid enters through a controlled feed line. Carbon dioxide enters under pressure through diffusers or contact surfaces. The gas breaks into fine bubbles and dissolves into the cola. The system controls pressure, liquid temperature, and gas flow, so every batch reaches the target carbonation level. The beverage is chilled before carbonation. It passes through a plate heat exchanger, where thin stainless steel plates separate the cola from a cold circulating fluid. Heat leaves the beverage rapidly. The liquid exits cold, dense, and ready to absorb gas. Some lines remove dissolved air before carbonation. In a deaeration unit, the flat drink moves under reduced pressure. Tiny air bubbles separate from the liquid and are pulled away. This makes carbonation more consistent and helps the drink hold its sparkle after sealing. The flat Pepsi comes from a blending system. Treated water and concentrated syrup meet at a proportioner. The syrup line is dark, sweet, and strong. The water line is clear and neutral. Flow meters measure both streams, and automatic valves adjust the ratio continuously. As the two streams combine, the syrup thins into finished strength cola. The color remains deep brown, but the flavor, sweetness, acidity, and body shift into the final beverage balance. This flat cola moves directly toward chilling, deaeration, and carbonation. The syrup is made in a separate syrup room. Treated water enters a stainless steel mixing tank. Sweetener is added first. It may arrive as liquid sweetener or as sugar dissolved into the water. The tank agitator keeps the base moving so no dense layer forms at the bottom. When sugar crystals are used, they fall into the water and gradually disappear. The mixture becomes heavier and glossy as the solids dissolve. Recirculation pumps may draw syrup from the bottom and return it near the top, creating a uniform sweet base. The sweet base passes through filtration before flavoring. Fine screens or filters remove undissolved material. Clean syrup protects proportioning valves, pumps, and filling equipment later in the process. Pepsi concentrate then enters through a closed dosing line. Caramel color spreads through the sweet base. Acids and flavor components blend into the liquid. The tank changes from clear syrup into a dark cola concentrate. The agitator turns steadily until the batch is uniform from the surface to the outlet. The finished syrup is much stronger than the drink itself. It is held in a tank with slow agitation. Pumps send it forward only as the proportioner requires it. The syrup flow and treated water flow create the finished cola continuously during production. The treated water begins as incoming plant water. It moves first through particulate filtration to remove suspended solids. It then passes through activated carbon, which reduces unwanted taste and odor. Additional polishing steps create a consistent water base for syrup making and final blending. This water matters because it makes up most of the beverage. Its clarity, taste, and mineral balance must stay steady. Sensors monitor flow, pressure, and treatment performance before the water enters storage tanks. While the liquid side is prepared, containers move through their own system. Aluminum cans arrive empty, lightweight, and open at the top. They are already formed and printed before entering the filling hall. The cans feed from depalletizers into single-file lanes. Air conveyors and guide rails control their movement without crushing the thin walls. Before filling, the cans are rinsed. They invert, receive a blast of filtered air or treated rinse water, drain, and return upright. This removes loose particles from the interior before the cola enters. PET bottles follow another route. They often begin as preforms. A preform is a short, thick plastic tube with a finished threaded neck. The body has not yet been expanded. The preforms enter a heating oven and rotate beneath infrared lamps so the plastic warms evenly. A heated preform enters a blow mold. The mold closes around it. A stretch rod pushes down through the center, pulling the softened plastic lengthwise. Compressed air then expands it outward until it touches the chilled mold walls. The base, shoulders, sidewall, and label panel form at once. The mold opens and the empty bottle exits by its neck ring. Air conveyors carry it forward. Because the bottle is light before filling, air jets can push it along while rails support the neck finish. The bottles pass through rinsing before filling. Each bottle is gripped, inverted, cleaned internally, drained, and returned upright. It then enters a pressure filler similar in purpose to the can filler, but matched to bottle geometry. For plastic bottles, the filling valve seals around the mouth. Pressure is balanced before liquid enters. Pepsi flows into the bottle with controlled turbulence. The fill level rises to the target height, and the valve closes. The filled bottle moves immediately to capping. Caps are sorted in an orienting bowl and sent down chutes to the capping heads. Each cap lands on the bottleneck and tightens to a controlled torque. The tamper band locks below the neck ring as the cap finishes turning. Glass bottles use a heavier container path. They pass through inspection before filling. Cameras and light systems check the mouth, base, sidewall, and interior. After filling, crown caps or threaded closures seal the bottle. The closure must hold carbonation pressure as the beverage warms and moves through packing. Every sealed container enters inspection. Fill level sensors check the liquid amount. Cameras inspect caps, can seams, bottle shapes, crown placement, dents, thread finish, and printed decoration. Any defective unit is removed automatically from the conveyor. Filled containers are often wet on the outside because the beverage is cold. Air knives remove condensation. Thin, high-speed sheets of air strike the cans and bottles from multiple angles. Droplets break away from lids, seams, shoulders, labels, and bases. Hershey's chocolate production begins when a thick brown chocolate mass is squeezed between refining rollers until its coarse texture becomes smooth enough for a finished bar. The mixture entering the refiner is not ready to mold. It contains cocoa ingredients, sugar, milk components, cocoa butter, and other fats blended into a heavy paste. The particles are still too large. If the bar were made at this stage, the texture would feel gritty instead of smooth. The refiner uses closely spaced rollers to reduce the particle size. The chocolate paste is pulled through narrow gaps under pressure. Each pass breaks down sugar crystals, cocoa particles, and milk solids into a finer structure. The paste becomes thinner in texture, more uniform, and better suited for the next stage. Before the chocolate reaches this point, the cocoa stream begins with roasted cocoa beans. The beans are cleaned, sorted, and roasted to develop flavor and loosen the outer shells. After roasting, the beans pass through cracking equipment. The brittle shells break away from the inner cocoa nibs. Winnowing equipment separates the lighter shells from the heavier nibs using airflow and screening. The nibs continue into grinding. As they are crushed, cocoa butter inside the nibs melts from the heat of friction, turning the dry pieces into a flowing cocoa liquor. This dark liquid becomes one of the main foundations of the chocolate. Milk chocolate production also needs milk ingredients. Milk powder or other prepared milk components are measured into the mixing system. Sugar is dosed separately. Cocoa butter or additional fat is added to control flow and texture. The ingredients come together in mixers that fold the dry and liquid phases into a uniform paste. This paste is the material that enters the refining rollers. Once refined, it moves into conching equipment. Conching is a long mechanical working stage. Heavy arms, rollers, or blades push and fold the chocolate continuously under controlled temperature. Inside the conche, the chocolate becomes smoother and more fluid. Fat spreads around the tiny dry particles. The mass loses rough edges in texture and develops the flow needed for molding. The movement is slow, heavy, and constant, like thick liquid being polished from inside. The chocolate's viscosity is adjusted during this stage. It cannot be too thick, or it will not flow cleanly into molds. It cannot be too thin, or it will not hold the correct bar structure. The conche brings the chocolate toward the exact behavior needed for high-speed depositing. After conching, the chocolate passes through storage tanks. These tanks keep it warm and moving. Slow agitators prevent settling and maintain even temperature. From here, the chocolate is pumped toward tempering. Tempering is the stage that prepares the chocolate to set correctly. The warm chocolate is cooled, then gently reheated through a controlled temperature curve. This creates stable cocoa butter crystals inside the liquid chocolate. Without proper tempering, the finished bar could become soft, dull, streaked, or weak. Properly tempered chocolate sets with a firm structure, smooth surface, and clean break. The liquid remains pumpable, but its internal crystal structure is ready for molding. The tempered chocolate flows into the molding line. Rows of empty bar molds move beneath depositor nozzles. The molds are usually made from rigid plastic or metal and contain the exact shape of the finished Hershey's bar, including its rectangular outline and raised segmented pattern. The depositor releases a measured amount of chocolate into each mold cavity. The chocolate spreads across the base and into the corners. It fills the raised letter and segment details from below, because the mold holds the bar pattern in reverse. The molds pass through a vibrating table immediately after filling. The vibration settles the chocolate and removes trapped air bubbles. Small bubbles rise to the surface and break. The chocolate levels out, filling every corner and detail of the mold. The filled molds now enter a cooling tunnel. Chilled air flows around them while the chocolate begins to crystallize. The surface touching the mold firms first. The center of the bar sets more slowly. The stable crystals created during tempering guide the full bar into a solid structure. Cooling must be carefully controlled. If it is too fast, the bar can contract unevenly or form surface defects. If it is too slow, the chocolate remains soft and cannot release from the mold cleanly. The tunnel balances air temperature, humidity, and travel time. As the bar cools, it contracts slightly. This small shrinkage helps it separate from the mold surface. When the mold reaches the demolding area, the chocolate is firm enough to release without bending. The molds invert or flex lightly. Mechanical taps or vibration help the bars drop onto a conveyor. Each bar lands with its molded face upward or is turned into the correct orientation for wrapping. The surface now shows the familiar segmented shape. The empty molds return to the filling station. They may pass through inspection or cleaning before receiving the next chocolate deposit. The molding loop continues continuously, with empty molds becoming filled molds, cooled molds, demolded molds, and empty molds again. The demolded bars move through inspection. Cameras check shape, surface marks, missing corners, air holes, dull patches, broken segments, and incorrect release. Bars outside the program limits are removed automatically. Metal detection scans the product stream before wrapping. Accepted bars continue toward the wrapping line. Timing belts space them evenly. Guide rails align each bar lengthwise. The wrapper must meet every bar at the same position, so spacing and orientation are tightly controlled. For a standard chocolate bar, printed wrapper film or foil-backed material unwinds from large rolls. Tension rollers keep the material smooth. Registration sensors read printed marks so the wrapper design lines up correctly with the chocolate. The bar enters a flow wrapping system. The wrapper folds around it to form a tight package. A longitudinal seal closes along the back or underside. Heated sealing wheels press the material together while the bar continues forward. Cross-seal jaws close the two ends of the wrapper. They seal and cut the package from the continuous film. Each wrapped bar leaves as a separate unit with the chocolate protected inside. Some Hershey's bar formats use an inner wrap and an outer paper band. In that route, the chocolate first receives a protective foil or film layer. Then a printed paper wrapper folds around the outside. Folding plates, belts, and tucking fingers create crisp edges around the rectangular bar. Miniature bars follow the same basic idea on smaller equipment. Small molded pieces are aligned, wrapped in individual foil or film, sealed, coated, and sent toward bagging or carton packing. For bars containing inclusions, the chocolate process changes before molding. Almonds, crisped rice, cookie pieces, or other inclusions are prepared separately and fed into the tempered chocolate stream or deposited into the molds. The pieces must be dry and correctly sized so they do not clog nozzles or create weak spots. When inclusions are mixed into the chocolate, gentle agitation keeps them suspended. The depositor must deliver both chocolate and pieces evenly into every mold. The vibrating stage settles the mixture without allowing all inclusions to sink to one side. For filled or layered chocolate products, a shell molding process may be used. Chocolate is deposited into molds, then shaken or inverted to coat the cavity walls. After partial cooling, a filling is added, and more chocolate seals the base. The finished piece is cooled, demolded, inspected, and wrapped in a similar downstream sequence. For the classic solid bar, the process remains focused on molding a single continuous chocolate body. The segmented pattern helps the bar break into pieces later, but inside the factory, it also gives the product a precise shape that inspection systems can measure. Wrapped bars pass through check weighers. A missing bar, broken bar, or incorrect product weight causes rejection. Vision systems inspect wrapper position, seal quality, code presence, print alignment, and package damage. Celsius production begins with a small, concentrated solution that carries the drink's functional ingredients before the full beverage volume is created. A measured amount of treated water enters a stainless steel preparation tank. The tank is smaller than the final blending vessel because this stage is built for accurate dissolution rather than high volume dilution. The agitator starts first, pulling the water into a circular motion. Powdered and liquid ingredients can then enter without forming heavy pockets at the bottom. Caffeine is measured through a controlled dosing system. It may be added as part of a prepared ingredient blend or dissolved separately before entering the main preparation stream. The amount is small compared with the final drink volume, so the dosing equipment must be precise. The ingredient enters beneath the surface and disappears into the moving water. Vitamin ingredients follow through separate feed lines or prepared solution tanks. They are added in controlled amounts and mixed until the solution is uniform. The goal is a clear, even ingredient stream that can later be diluted across thousands of cans without variation. Other formula components enter in the same controlled way. Some arrive as liquids. Some are dissolved in small side tanks before being pumped forward. The preparation tank keeps the solution moving so every ingredient spreads through the water evenly. This concentrated functional solution then passes through filtration. Fine filters remove any undissolved specks before the stream reaches the main beverage blend. The liquid must remain smooth because particles can interfere with valves, meters, and filling equipment later in the process. While this solution is being prepared, the main water stream is also being conditioned. Incoming water passes through particle filtration to remove suspended material. Activated carbon removes unwanted taste and odor. Additional polishing equipment stabilizes clarity and mineral behavior. The treated water collects in sealed stainless steel tanks where sensors monitor temperature, level, and flow. A large blending tank receives the first measured charge of treated water. The agitator begins rotating slowly, then builds a steady circulation. The tank is polished inside, so the liquid moves smoothly with no rough surfaces or dead zones. Sweetener components are added according to the product formula. In Celsius, this may involve a low-calorie or sugar-free sweetening system rather than the heavy sugar syrup used in many traditional soft drinks. The sweetener stream is dosed carefully because small amounts can strongly affect the final taste. The sweetener dissolves into the treated water. The liquid stays light and clear. It does not become thick and syrupy like a full sugar cola base. The agitator keeps the mixture uniform, while sensors track the batch condition. Acid ingredients are added next. They create the sharp, bright structure that supports the flavor. A measured acid solution enters through a closed line. The moving water pulls it downward and spreads it through the full tank volume. Flavor concentrate follows. The specific variety determines the concentrate used. Citrus, berry, tropical fruit, peach, grape, watermelon, or other flavor systems can be connected to the same blending equipment. The concentrate enters in a small stream but changes the character of the entire tank. Color ingredients are added when the variety requires them. Some formulas remain nearly clear, while others receive a light tint. The color addition is tiny, but the mixing must be complete. A small streak in the tank would become an uneven product in the cans. The concentrated functional solution now enters the main blend. It is pumped from the preparation tank through filtered stainless steel lines. Flow meters verify the addition. The liquid joins the flavored, sweetened, acidified base and is folded through by the main agitator. The beverage is now close to finished, but it still needs final dilution control and carbonation. If the plant uses a concentrate and water system, the blend moves to a proportioning unit. One pipe carries the strong beverage base. Another pipe carries treated water. The proportioner measures both streams continuously. Automatic valves make constant corrections, so the finished drink remains at the target strength. The strong base thins into the final beverage as it meets the water inside a closed mixing chamber. The flat Celsius beverage then moves into cooling. It passes through a plate heat exchanger made of thin stainless steel plates. Cold fluid moves on the other side of the plates, pulling heat from the drink. The beverage temperature drops quickly without contacting outside air. Cooling prepares the drink for carbonation. Cold liquid absorbs carbon dioxide more efficiently. It also creates a calmer filling condition later. A warm carbonated beverage would foam too heavily when it entered the can. The chilled liquid may pass through a deaeration stage. Reduced pressure pulls dissolved air out of the beverage. Tiny bubbles rise and separate from the stream. This step improves carbonation behavior by reducing unwanted gas before carbon dioxide is added. Carbon dioxide enters through regulated gas lines. Pressure control equipment stabilizes the flow before it reaches the carbonator. Inside the carbonator, chilled Celsius meets carbon dioxide under pressure. The gas dissolves into the liquid, creating the sparkling texture of the finished drink. From this point onward, the beverage remains enclosed inside pressurized piping. The liquid is finished, carbonated, and ready for the canning line. Empty aluminum cans move through a separate preparation route. They arrive already formed and printed, open at the top. The cans are lightweight, thin-walled, and shaped to hold internal pressure after seaming. Guide rails arrange the cans into a steady single-file stream. The cans enter an air rinser, where curved rails invert them. Filtered air blasts the inside surface, removing loose particles. The cans rotate upright again and continue toward the filler. The rotary filler receives the cans through a star wheel. The star wheel spaces every can beneath a filling valve. Above the valves, the filler bowl holds chilled carbonated Celsius under controlled pressure. Each can aligns with its valve. The filling system controls pressure and flow so the beverage enters without excessive turbulence. The valve opens and the sparkling drink flows into the can. The liquid rises quickly while foam is kept low by cold temperature and controlled filling conditions. The valve closes at the target fill volume. A small headspace remains at the top of the can. This space is needed for proper sealing and pressure behavior after the lid is applied. The filled can moves immediately to lid placement. Aluminum lids feed from a stacked supply. A lid separator releases one lid at a time and positions it over the open can. The can then enters the seamer. The can body and lid rotate together while seaming rolls press the metal edges into shape. The first operation curls the lid edge around the can flange. The second operation compresses the folded metal into a tight double seam. This seam seals the carbonated drink inside without glue. The aluminum folds lock together mechanically, forming a pressure-tight closure. Sealed cans move directly into inspection. Fill level sensors verify the liquid amount. Cameras check lid placement, seam condition, printed surface quality, dents, and overall can shape. Any defective can is rejected from the conveyor by an air jet or mechanical pusher. Red Bull production begins with water being prepared before any flavor, sweetness, carbonation, or can ever enters the process. Incoming water first moves through a treatment system. It passes through filters that remove suspended particles. Activated carbon removes unwanted taste and odor. Additional polishing stages bring the water to a consistent clarity and mineral condition. The goal is a clean, neutral liquid that behaves the same way in every batch. The treated water flows into stainless steel holding tanks. These tanks are sealed and fitted with sensors that track level, temperature, and flow. Pumps draw water from the tanks and send it toward the blending area through closed sanitary pipework. A measured volume of treated water enters the first blending vessel. The agitator starts turning before the dry ingredients arrive. Its blades pull the water downward, push it outward along the tank wall, and create a steady circular movement through the entire vessel. Sugar is added into this moving water through a controlled dosing system. The crystals fall into the rotating liquid and begin dissolving. At first, the mixture looks slightly uneven. As agitation continues, the sugar disappears completely and the liquid becomes heavier, smoother, and more reflective. The sugar solution may be warmed slightly to speed dissolution. The heat is controlled because the drink must remain stable for later ingredient additions. The tank does not cook the liquid. It simply creates a smooth, sweet base with no gritty particles remaining. This sweetened base passes through fine filtration. Any undissolved material is removed before the liquid reaches the next blending stages. Clean filtration protects pumps, valves, meters, and filling equipment from blockage or uneven flow. The filtered liquid returns to the main blending line. Acid ingredients are prepared in a separate solution and metered into the moving stream. These acids give the drink its sharp, bright structure. The addition is small, but it affects the entire taste balance of the beverage. The agitator folds the acid solution through the sweet base. The liquid remains pale and clear. Unlike cola, there is no dark caramel color. Every ingredient must dissolve neatly because the finished drink has a light, translucent appearance. The functional ingredient stream is prepared next. Caffeine, taurine, vitamin components, and other formula ingredients are measured in controlled amounts. Some are added as ready-made liquid solutions. Others are dissolved in smaller preparation tanks before being pumped into the main blend. These ingredients enter through narrow stainless steel lines. Flow meters and dosing pumps control their addition. The amounts are precise because a small dosing error would affect a large volume of drink. Once added, the main agitator and inline mixers spread them evenly through the batch. Flavor concentrate is introduced after the base ingredients are dissolved. It enters as a small but powerful stream. The flavor must spread through the full tank without forming strong pockets. The mixing system keeps the liquid moving until the entire batch carries the same flavor intensity. If a colored Red Bull variety is being produced, color is added through another metered stream. A small amount changes the appearance of the whole tank. The color disperses until the liquid is uniform from the top surface to the bottom outlet. The beverage base is now sweetened, acidified, flavored, and fortified with its dissolved ingredients. It is still not finished. It has no carbonation, and its temperature is not yet ideal for filling. The blended liquid moves toward a proportioning system if the process uses a concentrated base. One pipe carries the strong blend. Another pipe carries treated water. Flow meters monitor both streams continuously. Automatic valves adjust the ratio so the final drink strength stays constant. Inside the mixing chamber, the concentrated base and treated water combine. The drink reaches its final dissolved ingredient level. It is now the correct flavor, sweetness, acidity, and appearance, but it is still flat. The flat beverage enters a heat exchanger. It flows through narrow channels inside stainless steel plates. On the other side of those plates, chilled liquid removes heat. The drink cools quickly while remaining sealed from outside air. Cold liquid absorbs carbon dioxide more efficiently than warm liquid. Cooling also prevents excessive foam during filling. If the beverage were too warm, gas would escape too easily when it entered the can. The chilled drink may pass through a deaeration vessel. Reduced pressure pulls dissolved air out of the liquid. Tiny bubbles rise and separate from the stream. Removing excess air helps the carbon dioxide dissolve more cleanly and gives the beverage more stable carbonation behavior. Carbon dioxide enters through regulated gas lines. The gas passes through pressure control equipment before reaching the carbonator. Inside the carbonator, chilled Red Bull meets carbon dioxide under pressure. The gas dissolves into the liquid, creating the sharp, sparkling texture of the finished drink. From this stage onward, the beverage stays inside closed pressurized pipes. It cannot be exposed to open air or low pressure before filling, because carbonation would escape as foam. While the drink is being made, empty aluminum cans are prepared on another line. The cans arrive already formed and printed with open tops. They are light, thin-walled, and designed to hold internal pressure after sealing. Guide rails organize them into single-file streams. The cans enter an air rinser. Curved rails invert each can. Filtered air blasts the interior to remove loose particles. The cans drain or clear, then turn upright again and continue toward the filler. The filler is a large rotary machine with many filling valves. Carbonated Red Bull enters the filler bowl under pressure. Empty cans arrive through a star wheel that spaces them perfectly beneath the valves. Each can moves into position. The filling system controls pressure and flow, so the carbonated beverage enters smoothly. The valve opens, and pale sparkling liquid drops into the can in a controlled stream. Foam is minimized by the cold temperature and pressure-balanced filling conditions. The liquid rises quickly inside the can. When the correct volume is reached, the valve closes. A small headspace remains at the top so the can can be sealed properly and hold internal pressure. The filled can moves immediately to the lid applicator. Thin aluminum lids are fed from a stacked supply and placed one by one over the open cans. The lid must arrive immediately after filling, so carbonation stays inside the package. The can enters the seaming machine. The can body and lid rotate together, while seaming rolls press the metal edges into shape. The first operation curls the lid edge around the can flange. The second operation compresses the folded metal into a tight double seam. This seam is the pressure-tight closure. It contains the carbonated drink without glue or heat sealing. The finished can leaves the seamer sealed and ready for inspection. Sensors check the fill level. Cameras inspect the lid, seam position, printed can surface, and overall shape. Seam inspection systems verify that the closure is properly formed. Any can outside tolerance is removed from the line by a fast reject mechanism. The accepted cans pass through a coding station. An inkjet printer marks production information on the base or another assigned area. The mark is applied while the can continues moving at high speed. Because the drink was chilled before filling, moisture may form on the can surface. Air knives blast thin sheets of high-speed air across the metal. Droplets are stripped from the lid, sidewall, and base. The cans must be dry before secondary packaging. The dry cans enter lane-dividing conveyors. Guide rails separate the flow into parallel rows. Timing screws and gates control spacing. Collators gather the cans into exact groups for multi-packs, trays, or cartons. For shrink-wrapped packs, plastic film feeds around each grouped set of cans. The loose bundle enters a heat tunnel. Hot air shrinks the film tightly around the can walls and pack corners. The film cools into a firm wrap that holds the cans together. For tray packs, a corrugated blank slides under the can group. Folding guides raise the sides around the base. The tray supports the cans from below. Film may then wrap around both tray and cans to create a stronger pack. For cartons, paperboard blanks feed from a magazine and fold around the grouped cans. Glue is applied to the flaps. Compression belts press the board together until the carton holds its shape. Finished packs move through inspection. Sensors check pack count, film position, carton closure, tray alignment, and code presence. Defective packs are diverted before palletizing. The accepted packs travel to the palletizer. Conveyors rotate selected packs, so each layer forms a stable pattern. A layer table gathers one full arrangement, squares the edges, and transfers it onto a pallet. Layer after layer builds upward. Each level is placed in a programmed pattern so the stack remains stable. Slip sheets may be added between layers when needed to improve load strength. Monster energy production begins with a concentrated ingredient base being built in a stainless steel batching tank. The tank receives a small volume of treated water first. The agitator starts before the ingredient streams arrive. Its blades create a strong inward pull, drawing liquid down through the center and sending it outward along the curved tank wall. This movement prevents heavy powders or dense liquid concentrates from collecting in one place. The water used in the batch has already passed through the plant treatment system. Incoming water is filtered to remove suspended particles. Activated carbon removes unwanted odor and taste. Additional polishing stages make the water clear and consistent. The finished water is stored in closed tanks before being pumped to the blending room. The first base addition is usually the sweetener system. Sugar, glucose syrup, or another specified sweetener stream is measured into the moving water. If dry sugar is used, it falls through a controlled feeder and disappears into the rotating liquid. If liquid sweetener is used, it enters as a thicker stream and folds into the water as the agitator turns. The sweetened liquid becomes denser. The surface changes from fast ripples to slower, glossy movement. Temperature may be raised slightly to help the sweetener dissolve, but the liquid is not cooked. The goal is a clear, smooth base that can carry the rest of the formula without gritty particles. This sweet base passes through fine filtration. The filter removes any undissolved sugar or small particles before the liquid reaches the precision ingredient area. Clean flow is important because later equipment depends on accurate metering through valves, pumps, and flow sensors. The filtered base returns to the main blending vessel. Acid ingredients are added through a metered line. They create the sharp structure behind the sweetness. The acid stream is small compared with the full batch volume, so it must be spread evenly. The agitator keeps the liquid moving until the acidity is uniform throughout the tank. The energy ingredient blend is prepared next. Caffeine, taurine, B vitamin components, and other formula ingredients are measured in smaller preparation vessels. Some ingredients arrive as liquids. Others are dissolved into water first, so they can enter the main tank as controlled solutions. Each addition is pumped through closed stainless steel lines. Flow meters track the amount. The ingredient streams enter beneath the surface, where the moving liquid immediately pulls them through the batch. The tank must distribute them evenly because the finished drink is filled at very high speed, with no chance to correct uneven concentration later. Flavor concentrate is then introduced. Monster varieties use different flavor systems depending on the product, so the same blending equipment can produce different versions by changing the programmed concentrate, color, and ingredient sequence. The concentrate enters in a small, powerful stream. The tank darkens, brightens, or shifts color depending on the variety. Color is metered separately when required. A small amount spreads through the entire batch and changes the appearance of the liquid. Greenish, golden, orange, blue, purple, or near clear varieties can be produced by changing this stream and the flavor system connected to it. The concentrated base is now strong, sweet, acidic, flavored, and loaded with dissolved ingredients. It is not yet the final beverage. It may be too concentrated for direct filling, so it moves toward a proportioning system where it will be diluted to finish strength. A second stream of treated water arrives from storage tanks. This water bypasses the small concentrate tank and moves directly toward the final blender. Flow meters measure both streams. One meter reads the concentrate flow, another reads the treated water flow. The proportioner adjusts both streams continuously. Automatic valves make small corrections whenever pressure or flow changes. The machine keeps the ratio locked so the drink has the same flavor strength, sweetness, acidity, and dissolved ingredient level from the first can to the last. Inside the final blending chamber, the concentrate and water combine. The intense base thins instantly. The drink reaches its final formula strength. At this stage, it is flat Monster Energy. It has color, sweetness, acidity, flavor, and dissolved energy ingredients, but it has no carbonation. The flat beverage flows into a cooling section. It passes through a plate heat exchanger, moving through narrow channels between stainless steel plates. Chilled fluid travels on the opposite side of the plates and pulls heat out of the drink. The beverage temperature drops quickly while the liquid remains sealed from outside air. Cooling prepares the drink for carbonation. Cold liquid absorbs carbon dioxide more effectively than warm liquid. Cold filling also helps reduce foam when the beverage enters the can. Before carbon dioxide is added, the beverage can pass through a deaerator. Reduced pressure pulls dissolved air out of the liquid. Tiny bubbles rise and separate from the stream. Removing excess air allows carbonation to behave more predictably and helps the drink stay consistent inside the sealed can. Carbon dioxide enters through pressure-regulated gas lines. The gas is filtered and controlled before reaching the carbonator. Inside the carbonator, chilled Monster Energy flows under pressure while carbon dioxide dissolves into it. The liquid becomes sparkling, but the gas remains trapped in solution because the system stays sealed and pressurized. From this point forward, the beverage must stay under controlled pressure. It moves through closed stainless steel piping toward the filler. Any sudden pressure drop would cause foaming and carbonation loss. While the drink is being blended and carbonated, empty cans move on a separate line. The aluminum cans arrive already formed, decorated, and open at the top. They are light, thin, and designed to hold internal pressure once sealed. The cans enter a lane-guided conveyor and move toward the rinser. Curved tracks invert each can. Filtered air blasts the interior to remove loose particles. The cans rotate upright again and continue toward the filling machine. They move in tight rows, with rails keeping them stable as they approach the star wheel. The rotary filler receives the cans one by one. The star wheel spaces them evenly and positions each can beneath a filling valve. Above the valves, the filler bowl contains chilled carbonated Monster under controlled pressure. The filling valve opens. The drink flows smoothly into the can. The liquid must enter without excessive turbulence. If it splashes too hard, foam rises and interferes with the fill level. The cold temperature and controlled pressure keep the fill clean. The can fills rapidly. A small headspace remains at the top. This space is necessary for proper sealing and pressure behavior after the lid is applied. The valve closes at the exact target volume, and the can moves immediately towards seaming. Aluminum lids feed from a stacked supply. The lid dispenser separates one end at a time and places it over each filled can. The can cannot remain open for long because carbonation would begin escaping. The seamer closes the package mechanically. The can body and lid rotate together. The first seaming roll curls the lid edge around the can flange. The second roll compresses the metal folds into a tight double seam. No glue is used. The pressure-tight seal is created by folded aluminum. The sealed cans travel directly into inspection. Fill level sensors verify the liquid amount. Cameras check the lid, sidewall, top surface, and printed body. Seam inspection systems examine the double seam. A can with a dent, low fill, high fill, weak seam, or missing code is rejected from the line. The accepted cans pass through a coding station. An inkjet printer marks the can with production information. The code is applied to the base or another assigned area while the can moves at full conveyor speed. Because the drink was chilled before filling, condensation can form on the can surface. Air knives blast narrow sheets of high-speed air across the lid, sidewall, and base. Water droplets break away so the cans enter, packaging dry. The dry cans move into lane dividers. Guide rails split the flow into parallel rows. Timing screws control spacing. Stop gates and collators gather cans into the correct pattern for secondary packaging. A naked Snickers center enters the enrober with its layers exposed. The bottom layer is pale nougat. The top layer is caramel packed with roasted peanuts. The sides show the cut structure clearly, with soft nougat below and darker caramel above. It already has the shape of a bar, but it is not finished until chocolate surrounds every exposed surface. The center rides on a wire mesh belt. Ahead of it, tempered milk chocolate circulates through a coating system. A pump lifts the chocolate into an overhead trough. From there, it falls as a smooth curtain across the full width of the conveyor. The center passes through the curtain. Chocolate flows over the peanut caramel top first, then down the sides and across the cut ends. At the same time, a lower coating stream covers the underside through the open mesh belt. The bar becomes enclosed from all directions. Excess chocolate drains away through the belt and returns to the reservoir. Air blowers remove extra coating from the top and edges. The airflow smooths the surface and controls shell thickness. Too much chocolate would bury the shape. Too little would expose peanuts, nougat, or caramel. A short vibrating section helps the chocolate settle. Tiny air bubbles rise from the coating. The liquid shell rounds the corners and fills small uneven spaces around peanuts near the surface. The bar now looks finished, but the chocolate is still soft. Before this enrobing stage, the center is built as a wide layered slab. The nougat layer begins with a cooked sugar syrup. Sugar, glucose syrup, and water are measured into a cooker. Heat drives off moisture, making the syrup thicker and more concentrated. The syrup must reach the correct solids level because it controls the chew and stability of the nougat. In a separate mixer, an aerating base is prepared. A whipping ingredient is hydrated and beaten until it can hold fine air bubbles. The hot syrup streams into this foam while the mixer turns. The foam becomes stronger and heavier as the syrup blends through it. The mixture changes from light foam into dense confectionery nougat. It traps many small air cells, giving the layer a softer bite than caramel. Milk ingredients, fat, peanut flavor components, and other formula additions are folded in. The mixer works the mass until it becomes uniform. The nougat must be soft enough to bite through, but strong enough to support caramel and peanuts. If it is too weak, the bar compresses during cutting. If it is too dense, the center loses its light chew. The finished nougat leaves the mixer as a warm, elastic mass. It is deposited onto a forming belt. Rollers spread it into a continuous sheet. Side guides control width, and calibrated rollers set thickness. The surface becomes flat enough to receive the next layer. The nougat sheet enters a cooling section. Cool air firms its surface while the inside remains chewy. This prevents the caramel layer from sinking too deeply into it. The caramel layer is produced separately. Sugar, glucose syrup, milk ingredients, fat, and water enter heated kettles or continuous cookers. The mixture starts pale and fluid. As water evaporates, the liquid thickens, darkens, and becomes glossy. Agitators keep the mass moving so it cooks evenly. The caramel must have a stretchable texture. It needs to hold peanuts in place, but it also needs to pull, rather than snap when bitten. Cooking temperature, moisture level, and cooling temperature all control this behavior. Roasted peanuts are prepared on their own line before they reach the caramel. The peanuts pass through cleaning and sizing equipment. Screens remove small fragments and oversized pieces. Airflow pulls away skins and loose material. The accepted peanuts move into a roaster. Inside the roaster, hot air moves through the peanut bed. Moisture leaves the nuts. The texture becomes crisp. The peanuts develop the firmness needed to survive mixing and cutting without turning into powder. The roasted peanuts leave the heat and enter cooling. Air draws away heat quickly, stopping further roasting. After cooling, they pass through another screening stage. Broken pieces, skins, and undersized fragments are separated from the mainstream. The caramel and peanuts meet shortly before layering. Warm caramel flows through a mixing section, while peanuts are metered in at a controlled rate. The nuts become coated by caramel and spread throughout the mass. The mixture becomes thick, heavy, and textured. This peanut caramel mass is deposited across the cooled nougat sheet. A wide slot nozzle or depositor lays it down as a continuous band. Leveling equipment spreads it evenly from side to side. The peanuts must be distributed consistently so every cut bar contains the same type of layer. The two-layer slab now moves through a setting tunnel. Cool air firms the caramel enough for cutting. The slab remains flexible, but it can hold its shape under knives. The nougat, caramel, and peanuts bond into one continuous sheet. The slab reaches the slitting station. Long circular knives cut it lengthwise into narrow ropes. Each rope shows the same cross-section. The knives must pass through peanuts cleanly without dragging caramel down the sides. The ropes move apart slightly. A crosscutter then divides them into individual bar lengths. The blade moves in rhythm with the conveyor. Each cut produces a center with squared ends and exposed layers. The centers may pass through a conditioning zone before chocolate coating. Their surface temperature must match the enrobing conditions. Warm centers can make chocolate slide. Cold centers can make chocolate set before it spreads. The chocolate used for coating is prepared in another system. Cocoa ingredients, sugar, milk powder, cocoa butter, and fats are mixed into a thick chocolate mass. The mixture passes through refining rollers that reduce particle size. This creates a smooth texture instead of a gritty one. The refined chocolate moves into conching equipment. Heavy arms work the mass under controlled heat. Fat spreads around the dry particles. The chocolate becomes smoother and more fluid. Before the chocolate reaches the enrober, it is tempered. It is cooled and gently warmed through a specific temperature sequence. This creates stable cocoa butter crystals. Tempered chocolate sets into a firm shell with a smooth surface after cooling. The conditioned Snickers centers then enter the enrober, where the chocolate curtain covers them completely. After the blowers and vibration section, the coated bars move into the cooling tunnel. Chilled air flows around the bars from above and below. The chocolate begins to crystallize. The surface changes from liquid shine to a firm shell. The soft nougat and caramel remain inside, protected by the coating. Cooling is controlled carefully. If it is too fast, the shell can crack or look dull. If it is too slow, the bars smear on belts and guides. The tunnel balances belt speed, temperature, and airflow until the coating is stable. At the exit, the bars pass through inspection. Cameras check coating coverage, broken corners, exposed caramel, exposed nougat, surface marks, incorrect length, and deformed shape. Metal detectors scan the product stream. Bars outside the programmed limits are rejected automatically. Accepted bars move toward wrapping. Timing belts space them evenly. Guide rails align each bar lengthwise so it enters the wrapper straight. Printed film unwinds from a roll. Tension rollers keep the film smooth. Registration sensors read printed marks and synchronize the wrapper graphics with each bar. The film folds around the bar through a forming box. A longitudinal seal closes along the underside or back. Heated sealing wheels press the film layers together while the bar continues moving. Cross-seal jaws close the front and back ends of each pack. They seal and cut at the same time, separating one wrapped Snickers from the continuous film tube. Wrapped bars pass through check weighers. A broken bar, missing bar, or incorrect product creates a weight outside the target range and is rejected. Vision systems inspect seal quality, wrapper alignment, code placement, and print registration. A coding unit applies production information to the wrapper or outer pack. The mark is small, sharp, and placed while the pack moves at full speed. Single bars may move directly to case packing. Multi-pack formats branch into another grouping stage. Several wrapped bars are gathered by belts and mechanical guides. The group enters a secondary film wrapper or paperboard carton. M&M's pieces gain their hard candy shells through repeated polishing, coloring, and drying cycles inside large rotating pans. The chocolate centers arrive at this stage as small, rounded cores. They are already formed, cooled, and firm enough to tumble without flattening. The centers enter wide coating pans that rotate at a steady angle. As the pan turns, the centers climb up the inner wall, slide back down, and roll over each other in a continuous shifting bed. A sugar syrup is added in very thin amounts. It does not pour in heavily. It enters as a controlled stream or fine spray. The syrup touches the moving centers and spreads across their surfaces. Drying air flows through the pan, removing moisture from that layer. The syrup hardens into a thin shell. The cycle repeats again and again. A small dose of syrup coats the centers. The pieces tumble. Air dries the surface. Another dose follows. Each layer adds thickness. The round centers gradually become slightly larger, smoother, and stronger. This is how the shell is built, not in one thick coat, but in many thin, hardened layers. At first, the shell is plain and pale. Later, color is added to separate batches. Red pieces receive red syrup. Yellow pieces receive yellow syrup. Blue, green, orange, and brown batches move through their own color systems. Each color must remain separate until blending, because the coating pans create one color at a time. The pan speed controls the shape. If the movement is too slow, pieces may stick together or develop flat spots. If it is too fast, they can chip or bounce unevenly. The pan turns just enough to keep the candy rolling smoothly while the coating dries. Drying air is just as important as syrup. If the air is too weak, the pieces stay wet and clump. If it is too aggressive, the surface can roughen or dry before the coating spreads. Air temperature, humidity, and flow rate are balanced so the shell becomes hard, even, and glossy. Before these coating pans receive the centers, the chocolate cores are made in a separate process. Chocolate mass begins with cocoa ingredients, sugar, milk ingredients, cocoa butter, and fats blended into a thick paste. The paste passes through refining rollers that reduce the particle size. Sugar crystals, cocoa particles, and milk solids become fine enough that the finished chocolate feels smooth instead of gritty. The refined chocolate enters conching equipment. Heavy mixing arms work the chocolate under controlled heat. The mass becomes more fluid as fat spreads around the tiny particles. The texture becomes smoother, and the chocolate develops the flow needed for forming centers. The chocolate then moves into tempering. Tempering controls the cocoa butter crystals inside the chocolate. The liquid chocolate is cooled and gently reheated through specific temperature stages. This gives the chocolate the ability to set firm and resist smearing during later coating. To form the centers, tempered chocolate is deposited into small molds or dropped in measured portions onto a cooling surface, depending on the product type. For classic milk chocolate M&Ms, the goal is a small, lentil-shaped center. The chocolate must settle into a rounded disc that is thick in the middle and thinner at the edges. The formed centers pass through cooling tunnels. Cold air removes heat, and the chocolate solidifies. The centers contract slightly as they set. Once firm, they release from molds or separate from the forming surface. They are then screened to remove broken pieces, doubles, or misshapen centers. Some M&Ms varieties need a different center. Peanut M&Ms begin with roasted peanuts. The peanuts are cleaned, sized, and roasted until their moisture drops and their texture becomes crisp. After cooling, they are coated with chocolate before shell building begins. Each peanut becomes the center around which chocolate and candy layers are added. Peanut butter centers use a prepared paste. Ground peanuts, sweetener, fat, and stabilizing ingredients are mixed until thick and smooth. The paste is formed into small cores, chilled, and coated with chocolate or candy layers depending on the line. Pretzel or crispy varieties use baked centers that must remain dry and strong before coating. For the classic chocolate type, the cooled chocolate centers are transferred toward the panning room. The centers are loaded into the coating pans by measured batch weight. The pans begin rotating and the first shell building layers are applied. A base syrup layer helps seal the chocolate. This prevents color syrup from interacting directly with the chocolate surface. The early layers also strengthen the center so it can tolerate many more coating cycles. The pieces are repeatedly wetted and dried until the shell reaches the required thickness. The surface becomes harder with each cycle. When enough base shell is built, color coding begins. Colored syrup layers add brightness and identity to the candy. Each batch continues tumbling until the color is even. The pieces must not show pale spots, streaks, or exposed base layers. The rolling action distributes syrup across the top, bottom, and edges of every piece. Because each candy is small and constantly moving, the final shell becomes smooth and rounded. After coloring, the pieces move into polishing. A polishing solution is added in tiny amounts while the candy tumbles. The surface becomes brighter and glossier. Friction between the pieces helps smooth microscopic roughness. The candy changes from matte-colored pellets into shiny finished M&Ms. The polished candies are discharged and cooled. They move through screens that separate out small fragments, oversized clusters, chipped pieces, and dust. The accepted pieces continue by color into holding bins. The white letter is added after the shell is complete. The candies move into a printing system that orients and contacts the pieces quickly. A food-grade white marking material is transferred onto one side of each candy. The printing mechanism must apply the mark without cracking the shell or smearing the surface. Because M&Ms are rounded and small, perfect orientation is difficult. The system uses controlled feeding, vibration, and contact printing to mark the moving pieces at high speed. The printed candies pass through a short drying section, so the letter sets before blending and packaging. Different colors are then blended. Each color stream feeds from its own hopper. Vibrating feeders meter red, yellow, green, blue, orange, and brown pieces into a common conveyor or blending drum. The ratios are controlled so each finished package receives a balanced mix. The blending must be gentle. The shells are hard, but they can still chip if dropped too far. or crushed between equipment surfaces. Conveyors, chutes, and drums are shaped to keep the pieces moving smoothly. The mixed candies enter the weighing system. For small bags, a multi-head weigher divides the candy into several weigh buckets. Each bucket holds a small portion. The machine calculates which bucket combination equals the target weight, then releases those portions together. The selected candy drops into the bagging machine. Printed film unwinds from a roll and moves around a forming tube. The film edges meet and seal vertically, creating a tube. The candy falls through the tube into the open package. Horizontal sealing jaws close the bottom of one package and the top of the previous one. The jaws also cut the packages apart. Each bag leaves sealed, filled, and separated from the film web. For larger stand-up pouches, film is formed with gussets that allow the bag to stand. The pouch is filled by weight, sealed at the top, and cooled at the seal area so the closure holds cleanly. Resealable formats receive a zipper strip integrated into the film before the top seal is completed. For small tubes, cartons, or theatre boxes, the packaging path changes. Paperboard blanks open into box shapes. Candy is weighed or volumetrically metered into each carton. Flaps fold in sequence and lock or glue shut. The package then moves through inspection and coding. For bulk formats, candies are filled into larger bags or tubs. The filling system uses wider chutes and heavier weighing equipment. The same controls apply correct weight, clean closure, shell protection, and consistent color blend. Every package passes through inspection. Check weighers verify that the amount of candy is within the target range. Metal detectors scan the package. Vision systems check seal quality, print alignment, code presence, bag shape, and carton closure. Coding equipment applies production information to the bag, pouch, carton, or outer case. Inkjet or laser systems print while the package moves on the conveyor. A scanner can confirm that the code is readable. Accepted retail packs move into secondary packing. Bags may be counted and loaded into display cartons. Cartons may be grouped into corrugated cases. A case former opens a flat blank or folded case, seals the bottom, and presents it for loading. Mechanical pushers or pick-and-place systems load the retail packs into the case. The arrangement depends on package shape. Flexible bags need gentle compression. Boxes stack more tightly. Pouches may stand upright or lay flat in rows. A Cheerios ring begins as pressure trapped inside cooked oat dough. The dough is not shaped like cereal at first. It starts as a dense, warm mass made from whole grain oat flour, water, starches, sugar, salt, and small measured ingredients that help the cereal cook, expand, toast, and hold its shape. The entire process is designed to turn heavy grain into a light ring with a crisp wall and a hollow center. Whole oats arrive at the mill and pass through cleaning equipment. The oats move across vibrating screens that separate dust, broken pieces, and oversized material. Air currents lift away light chaff. Magnets remove tiny metal fragments. The cleaned oats continue into dehulling machines. Each oat kernel has a tough outer hull. The hull must be removed before the grain can become cereal flour. Dehulling equipment cracks and loosens the outer shell while keeping the inner groat usable. The separated hulls are pulled away by air and screening systems. The oat groats then move into milling equipment. Rollers and grinders reduce the groats into whole grain oat flour. The flour is not a fine bakery powder only. It must have the correct particle size for cooking, hydration, and extrusion. Too coarse, and the dough will not form smoothly. Too fine, and the dough may become sticky and difficult to shape. The oat flour is stored in silos or bins before mixing. Pneumatic conveyors move it through enclosed pipes using air pressure. The flour flows like a pale, dry stream into weighing systems. Load cells measure each batch before it enters the mixer. In the mixing area, oat flour meets water. The dry flour darkens slightly as it hydrates. Mixers turn with heavy paddles or rotating arms, folding the ingredients into a damp, thick dough. Sugar, salt, starch, and other dry ingredients are added in controlled amounts. The mixture becomes heavier as the oat particles absorb moisture. This is still only the first stage. The dough must be cooked before it can puff into the familiar ring. The hydrated mixture enters a cooker or preconditioner. Steam and heat soften the oat starches. The dough thickens and becomes more plastic. Inside the machine, rotating screws move the material forward while mixing and compressing it. Heat gelatinizes starch, which means the starch granules absorb water, swell, and form a cooked structure. The cooked dough is dense and smooth. It no longer behaves like flour and water. It behaves like a warm paste with enough strength to hold pressure. This cooked mass is the base that will later expand. The dough then moves toward the extruder. The extruder is a long barrel fitted with one or more rotating screws. The screws grab the cooked dough and push it forward. As the dough travels through the barrel, pressure builds. Friction, steam, and controlled heating keep it hot and workable. The end of the extruder contains the die. This die is the key to the Cheerios shape. It has small openings designed to form the ring. The cooked dough is forced through these openings under pressure. As it exits, the pressure drops suddenly. Moisture inside the hot dough flashes into steam, causing the material to puff. The cereal emerges in tiny ring shapes. The center hole is formed by the die geometry. The dough expands outward, but keeps the circular structure. The fresh pieces are soft, warm, and not fully crisp yet. They look like cereal, but they still contain too much moisture. A cutting mechanism slices the extruded rings to the correct thickness. The cutter moves rapidly across the die face or rotates in front of it. Each cut releases another small ring. The pieces drop onto a conveyor in a steady stream. At this point, the rings are fragile. They must be dried before they can be toasted properly. The cereal enters a drying system, where warm air removes moisture gradually. The rings tumble or travel over perforated belts, while heated air passes through them. Moisture leaves the surface first, then moves from the center of each piece outward. Drying must be controlled carefully. If the outside dries too fast, the ring can crack. If it stays too moist, it will not toast evenly. The goal is a stable cereal piece with enough structure to survive the next high heat stage. After drying, the rings enter the toaster. This is where the pale oat pieces become crisp and lightly browned. Hot air moves around the cereal as the pieces tumble or ride through the oven. The surface dries further, the texture becomes brittle, and toasted oat aromas develop. The ring wall changes during toasting. It becomes lighter, firmer, and more porous. The cereal snaps more cleanly when broken. The color shifts from pale beige to a warmer golden tone. Every piece must reach the correct balance of crispness and moisture. The toasted cereal exits the oven and enters a cooling zone. Air flows across the rings to remove heat. Cooling prevents condensation inside later packaging. It also stabilizes the texture before coating or final handling. Some Cheerios varieties move through a coating drum after toasting. For plain Cheerios, this step may be minimal compared with flavored versions. For sweeter or flavored varieties, syrup, flavor, honey, sugar, cocoa, fruit flavor, or other coating systems can be applied. In a coating drum, cereal rings tumble, while a liquid coating sprays onto them. The drum rotates slowly, lifting and folding the cereal so the coating spreads evenly. Nozzles atomize the syrup into fine droplets. The droplets hit the moving rings and cling to the surface. After coating, the cereal may pass through another drying stage. Warm air removes water from the coating and locks it onto the ring. The surface becomes dry enough that pieces do not stick together. The cereal keeps its separate, free-flowing form. The rings then move through screening equipment. Broken pieces and fines fall through mesh openings. Oversized clumps are separated. Airflow may lift away light dust. The goal is an even stream of properly formed rings moving toward packaging. Inspection systems check the cereal before it enters the bagging area. Optical sorters can detect unusual color, dark pieces, or shape defects. Metal detectors check the flow for unwanted fragments. Any rejected material is removed automatically from the product stream. The accepted cereal travels to large holding bins above the packaging machines. These bins act as buffers. They keep the packaging line supplied even as upstream cooking and toasting continue at a steady rate. The cereal flows downward by gravity into weighing systems. Multi-head weighers divide the cereal into small portions. Each weighing bucket holds a measured amount. The control system combines several buckets to reach the exact package weight. Once the correct combination is selected, the gates open and the cereal drops into a forming tube. The inner bag is made from a roll of flexible packaging film. The film unwinds, bends around a forming collar, and becomes a vertical tube. A heat sealer closes the back seam. The weighed cereal drops into the tube. Then horizontal seal jaws close across the top and bottom, creating a sealed bag. The bag must protect the cereal from moisture. Crisp cereal becomes soft if it absorbs water from the air. The film barrier and sealed seams help keep the texture stable. The filled inner bag moves toward the cartoning machine. Flat paperboard blanks feed from a magazine. Each blank is opened into a rectangular box shape. The cereal bag is inserted into the open carton. Mechanical guides keep the bag upright while the carton folds around it. The bottom and top flaps are closed by folding rails. Adhesive or locking tabs secure the carton. The box passes through compression belts that press the flaps into place. The carton becomes square, firm, and ready for coding. A coder prints production information on the box. The mark may include a batch code, plant code, line code, and time reference. The print head applies the code quickly as each box passes. Finished boxes move through check weighers. A box that is too light or too heavy is rejected. Vision systems can check flap closure, print position, and carton orientation. Proper boxes continue into case packing. Frosted flakes begin as hard corn grits entering a pressure cooker. The grits are not flakes yet. They are small broken pieces of corn endosperm, selected for size, hardness, and cooking behavior. Each piece must be strong enough to survive handling, but soft enough to flatten after cooking. The entire factory sequence is built around changing those dense corn particles into thin, toasted flakes with a dry sugar coating. Before cooking, the corn grits pass through cleaning and sorting equipment. Vibrating screens remove fines and oversized pieces. Air separators lift away light dust. Magnets pull out tiny metal fragments. Optical sorters can remove discolored particles. The goal is a clean, even stream of grits with a narrow size range. The cleaned grits move into weighing hoppers. Load cells measure each batch. Water, sugar, salt, malt flavoring, and other formula ingredients are prepared in separate feed systems. The ingredients must enter the cooker in the correct ratio because the corn needs to absorb moisture and flavor evenly before it can become a flake. The cooker is a sealed vessel built to handle heat and pressure. Corn grits enter through the top or side. Water and flavoring ingredients follow. The vessel closes and steam begins heating the mixture. Inside, the grits absorb moisture. Their hard centers soften. Starch granules swell and begin gelatinizing. The cooker rotates or mixes the batch so every corn particle receives heat and moisture. The movement is slow and heavy. The grits scrape, tumble, and roll inside the vessel while steam pressure builds around them. At the start, each piece is firm and dry. By the end of cooking, each piece has become flexible and slightly sticky. Cooking is one of the most important stages. If the corn is undercooked, it will crack instead of flattening. If it is overcooked, it can smear during flaking. The target is a cooked grit that is soft through the center, but still strong enough to become a distinct flake. After cooking, the hot grits discharge from the cooker. They are now darker, moist, and tender. They do not yet look like cereal. They look like swollen pieces of cooked corn. Steam rises from the mass as it spreads onto conveyors. The cooked grits move into a tempering stage. Tempering allows moisture to equalize inside each piece. The outside of a cooked grit may be wetter than the center. Resting time lets moisture migrate inward and outward until the particle becomes more uniform. This makes flaking smoother. During tempering, the grits sit in bins or move slowly through controlled holding equipment. The temperature and moisture continue balancing. The texture becomes less sticky and more elastic. Each grit becomes ready for flattening. Next comes the flaking mill. Two large steel rolls sit close together with a narrow gap between them. The rolls rotate toward each other. Cooked grits feed into the gap in a controlled layer. Each grit is caught between the rolls and squeezed flat in an instant. The transformation is sharp and mechanical. A thick corn piece becomes a thin flake. The pressure spreads the softened starch outward. The shape becomes irregular, with slightly uneven edges. These irregular edges give frosted flakes their natural-looking flake shape. The roll gap controls thickness. If the gap is too wide, the flakes remain thick and dense. If it is too narrow, they may tear or become too fragile. The mill must flatten the grits enough to create crisp flakes, while keeping them strong enough to travel through the rest of the line. Freshly rolled flakes are pale, moist, and flexible. They bend instead of snapping. They need heat to become crisp. The flakes enter a drying stage before toasting. Warm air removes part of the moisture. The flakes travel over perforated belts or through rotating dryers while air passes through the moving bed. Moisture leaves the flake surface first, then moves from the interior outward. Drying prepares the flakes for the toaster. It reduces stickiness and keeps the flakes separate. It also helps the toaster create a crisp texture rather than a leathery one. The flakes become lighter and less flexible as they dry. The toaster is where the cereal develops its final base texture. Flakes enter a high-temperature oven or rotary toaster. Hot air surrounds them. The flakes lift, tumble, and move through the heating zone. Their surfaces brown slightly. Their moisture drops further. Starch structure sets into a brittle form. The sound inside the toaster is dry and constant. Thousands of flakes move against metal surfaces and against one another. The pieces become lighter, crisper, and more aromatic as the heat passes through them. Toasting must be carefully controlled. A flake that is too pale may taste underdeveloped and soften quickly. A flake that is too dark can taste scorched. The target is a golden toasted cornflake with a dry snap and enough strength for coating. After toasting, the flakes pass through cooling air. Cooling stabilizes the cereal before frosting. If sugar coating hits flakes that are too hot, it can spread too quickly or become uneven. If the flakes are too cool or too dry, coating adhesion can change. The line controls the temperature before the next transformation. The frosting system begins with sugar syrup. Granulated sugar and water are combined in a syrup tank. Heat dissolves the sugar. The liquid turns clear and glossy. The syrup may include flavoring and small formula ingredients that help the coating dry correctly. Agitators keep the syrup uniform, while temperature control keeps it pumpable. The syrup must have the right solids level. If it is too thin, it will soak into the flakes and make them limp. If it is too thick, it may form heavy spots or clumps. The syrup must spray evenly and dry into a thin frosted layer. The toasted flakes enter a rotating coating drum. The drum turns slowly, lifting the flakes and letting them fall in a continuous curtain. Spray nozzles aim heated sugar syrup into the tumbling cereal. The syrup hits the moving flakes as fine droplets. the coating does not cover every flake like paint in one pass. It builds through repeated contact. A droplet lands, spreads slightly, and sticks. Another rotation exposes a new surface. More syrup lands. The flakes roll over one another, distributing the coating across the batch. This is the key difference between plain corn flakes and frosted flakes. The toasted corn base receives a controlled sugar layer that dries into a pale, crystalline finish. The coating adds sweetness, surface texture, and the slightly rough frosted look. The coated flakes leave the drum tacky and warm. They cannot be packed yet. They would stick together and lose crispness. They enter a finishing dryer. Warm air passes through the coated cereal. Water evaporates from the sugar syrup. The coating changes from sticky liquid to dry crystalline film. The flakes separate again as the surface hardens. The cereal becomes free-flowing, crisp, and lightly glossy. The drying step must remove enough moisture to protect crunch. Too much remaining moisture makes the cereal clump. Too much drying can make flakes brittle and powdery. The system balances air temperature, airflow, bed depth, and residence time. After drying, the frosted cereal moves into a cooler. Ambient or conditioned air brings the temperature down. Cooling prevents moisture condensation inside packaging. It also strengthens the sugar coating so it can survive conveyors, hoppers, and weighers. The cooled flakes pass through screening systems. Small broken flakes and sugar dust fall through mesh screens. Oversized clusters are separated. Airflow can remove light fines. The cereal stream becomes more uniform before inspection. Inspection equipment checks the flakes as they move toward packaging. Metal detectors scan the flow. Optical systems can detect dark flakes, pale flakes, clumps, and unusual particles. Reject gates or air jets remove material that does not match the set limits. The accepted cereal flows into surge bins above the packaging machines. These bins keep the packaging line supplied while the cooking, flaking, toasting, and coating systems continue running. The flakes drop from the bins into weighing equipment. Multi-head weighers measure the cereal by combining small portions from several buckets. Each bucket holds a different amount. The control system chooses the best combination to reach the package weight. Gates open, and the measured cereal drops downward. The inner bag forms from a roll of flexible film. The film unwinds and wraps around a forming tube. A vertical heat seal closes the back seam. The measured frosted flakes fall into the open tube. Horizontal sealing jaws close across the film, forming the top of one bag and the bottom of the next. The sealed bag protects the flakes from moisture. This is critical because the cereal's crisp texture depends on staying dry. The sugar coating also needs a barrier from humid air. Lucky Charms production starts with two separate product streams moving toward one final blend. One stream becomes toasted oat cereal. The other becomes dry, colourful marshmallow pieces. They are manufactured apart because they behave completely differently. The oat cereal needs heat, pressure, shaping, drying, and toasting. The marshmallow pieces need syrup cooking, aeration, colouring, shaping, and controlled drying. Only after both streams are stable can they be mixed without breaking or sticking. The cereal stream begins with whole grain oats. The oats are cleaned before they are milled. They move across vibrating screens that remove dust, small broken material, and oversized particles. Air separators pull away light chaff. Magnets catch small metal fragments. The cleaned oats continue into dehulling and milling systems. The outer hull of the oat is removed to expose the usable groat. The groats are then milled into oat flour. The flour must have a controlled particle size. It cannot be too coarse, or the dough will form rough, weak pieces. It cannot be too fine, or the mixture can become sticky and difficult to move through cooking and extrusion equipment. The oat flour is stored in bins before mixing. Pneumatic conveyors move it through enclosed lines using air pressure. The flour enters weigh hoppers, where the batch is measured. Small ingredient systems add sugar, salt, starches, and other dry components. Water enters through a metered line. Inside the mixer, the dry oat flour changes into a damp dough. Heavy paddles fold the water into the grain. At first, the mixture looks loose and uneven. As hydration continues, the particles swell and bind together. The dough becomes heavier, warmer, and more uniform. The hydrated dough moves into a cooker or preconditioner. Steam heats the mixture, while rotating screws or paddles keep it moving. The oat starch absorbs water and gelatinizes. This step gives the dough the plastic structure needed for shaping. Without proper cooking, the cereal would crumble instead of expanding cleanly. The cooked dough leaves the preconditioner and enters an extruder. The extruder barrel contains rotating screws that push the dough forward. Pressure rises as the material approaches the die. Heat and pressure work together, turning the dough into a compact, elastic mass. The die at the end of the extruder gives the cereal its shape. Lucky Charms cereal pieces are not simple rings like some oat cereals. They are small shaped pieces, often with curved or clover-like forms. The die openings control the outline. As the hot dough exits the die, pressure drops quickly and moisture inside the dough flashes into steam. The pieces puff slightly as they are cut. A rotating knife slices the extruded dough into small cereal shapes. Each cut releases another piece. The pieces fall onto a conveyor while still warm and soft. They already have their basic shape, but they are not yet crisp. The cereal pieces enter a dryer. Warm air passes around them to remove moisture. The drying must be gradual. If the surface dries too quickly, the pieces can crack. If too much moisture remains, the toaster cannot create a clean, crisp texture. The dryer turns soft oat shapes into firmer pieces that can handle toasting. The cereal then moves into a toaster. Hot air surrounds the pieces as they tumble or travel through the oven. The surface darkens slightly. The texture becomes brittle and light. Toasted oat aroma develops as moisture drops to the final range. The cereal becomes crisp enough to keep its shape in the box and in milk. After toasting, the cereal is cooled. Air flows across the pieces and carries away heat. Cooling prevents condensation in later packaging and keeps the texture dry. The cereal then passes through screens that remove fines, broken pieces, and oversized clusters. While the oat cereal is being formed, the marshmallow stream is built in a different part of the process. The marshmallow pieces begin with a sugar syrup. Sugar, corn syrup, and water enter a heated mixing vessel. The liquid warms and dissolves into a smooth syrup. The syrup must be concentrated enough to dry into a crisp structure, but still fluid enough to pump and whip. Gelatin or another aerating structure is prepared separately. It hydrates in water, then warms into a smooth solution. When added to the syrup, it helps the mixture hold air. The syrup is then moved into a whipping system. Air is worked into the syrup at high speed. The dense liquid expands into foam. Tiny bubbles fill the mixture, giving it a light interior. The foam becomes paler and thicker as air cells form. This is the opposite of the cereal stream, where pressure and heat create expansion. Here, mechanical whipping builds the internal structure. The marshmallow foam is divided into separate color batches. Each batch receives its own color and flavor system. The mixing has to be complete because streaks would show clearly in the finished pieces. The colors must remain strong after drying, so the wet foam is made more intense than the final dried piece may appear. The colored foam is shaped into the familiar, tiny marshmallow forms. It may be extruded through shaped dies, deposited into molds, or formed into sheets that are later cut. The shapes are small, with sharp edges and simple outlines so they can dry evenly and survive handling. Fresh marshmallow shapes are soft and sticky. They cannot be blended with cereal yet. They move into a drying system where warm, controlled air removes moisture. The surface firms first, then the interior dries. The pieces become lighter and more brittle as the water leaves. The drying step changes the marshmallow from soft foam into a crisp cereal inclusion. The finished piece is porous, colourful, and dry. It breaks with a light crunch instead of stretching. This texture allows it to remain separate in the cereal box. The marshmallow pieces are screened after drying. Dust, broken fragments, and misshaped pieces fall away. The accepted pieces move into storage bins. Each colour and shape can be held separately, then metered later into the final blend. Now the two streams come together. The toasted oat cereal flows from its holding bin. The marshmallow pieces flow from their own bins. Feeders meter each component into a blending drum or blending conveyor. The ratio must be controlled carefully. Too much cereal changes the appearance of the mix. Too many marshmallows can throw off weight distribution and packaging consistency. The blender moves gently. It lifts, turns, and folds the cereal with the marshmallow pieces without crushing them. This is important because the two components have different strengths. Toasted oat cereal is light, but more resistant to handling. Dried marshmallows are crisp and can fracture if the mixing is too aggressive. The blend becomes visually balanced as the colored pieces spread through the oat cereal. The machine does not grind or press the mixture. It simply turns the stream over itself until the distribution is even. After blending, the cereal passes through inspection. Metal detectors scan the product stream. Optical systems can identify dark cereal pieces, pale pieces, broken clusters, or foreign-colored particles. Screens remove dust and small broken fragments. Reject gates remove anything outside the limits. The finished Lucky Charms blend then enters surge bins above the packaging machines. The bins hold enough product to keep the packers running smoothly. The blend flows downward by gravity, but the hopper design must prevent separation. If the heavier cereal and lighter marshmallows separate too much, the final boxes would not contain a consistent mixture. Hard candy only has two useful states on a lollipop line: fluid enough to be shaped and glassy enough to hold its shape. Chupa Chups style production is built to push the candy through that transition at the exact moment a stick is inserted and locked, then isolate the finished piece from humidity so it never leaves the glassy state. The most reliable way to understand the factory is to start at the forming wheel, because every upstream system exists to feed that wheel at a stable rhythm. The forming wheel is an indexed machine with cavities that open, receive a dose of hot candy, accept a stick, close to shape, then release the lollipop. Its speed is fixed by output targets, so the candy mass must arrive at the depositor at the correct temperature and viscosity, and sticks must arrive at the inserter in the correct orientation and at the correct moment. Stick handling runs continuously. Sticks are cut to length if not pre-cut, then screened to remove splinters. A deburring or air cleaning stage strips dust because dust at the interface weakens bonding and creates voids. Sticks are then singulated into individual lanes. Singulation is a mechanical sorting problem. Sticks are light and can overlap, so feeders rely on vibration, step conveyors, and guide rails to separate them. Orientation is enforced, so the same end enters the candy each time. The stick feed ends at a pick-and-place head or pusher that inserts the stick into the cavity at a fixed depth. Depth stops are mechanical, so insertion depth remains consistent even if stick length varies slightly. Depth matters because too shallow reduces pull strength, and too deep can create internal stress rings that lead to cracking. While sticks are being fed, the candy mass is being prepared as a concentrated syrup that will set into a clear glass. Sugar is stored dry and screened so clumps do not enter dissolving. Water is filtered and tempered because inlet temperature affects dissolution speed and cook stability. Glucose syrup is held in jacketed tanks so viscosity stays stable for pumping, and it functions as a crystallization control ingredient. These streams combine in a dissolver, where heat and agitation create a clear solution. The target is full dissolution with no visible grains, because undissolved grains become nucleation sites that can trigger graining later, making the candy cloudy and brittle in an unpredictable way. Concentration is performed rapidly to reach hard candy solids. In a continuous system, the clear syrup is pumped through heated coils under pressure, allowing temperature to rise quickly without boiling inside the tube. A flash chamber then reduces pressure so a portion of water instantly vaporizes and exits as steam. This flash step tightens final moisture and also reduces thermal damage because water removal occurs at a lower effective temperature than extended open boiling. Final moisture content is the main structural setting. Too much moisture yields candy that stays tacky and softens quickly. Too little moisture yields candy that becomes overly brittle and cracks at the stick interface during cooling or later handling. Immediately after concentration, the mass enters a controlled cooling section. The aim is to bring the mass to a forming temperature that is still fluid enough to be deposited and shaped, but not so hot that it degrades flavor and not so cool that it begins to set in pipes. Heat exchangers and jacketed manifolds manage this temperature precisely. At this stage, additives are introduced because many flavors contain volatile compounds that would be stripped or damaged at peak cooking temperatures. Color is prepared as concentrated solutions or dispersions and filtered so no particles clog injectors or create specks. Flavor is metered by precision pumps into the candy stream. Injection is placed after the main heat load so aromatics are preserved. Acid can be introduced as a solution if the recipe calls for a sharper profile, but acid timing is controlled because acid accelerates sucrose inversion at high temperature, which changes viscosity and long-term stickiness. Mixing after injection is done with static mixers or low-shear mixing manifolds that fold the flow and eliminate streaks without entraining air. Air entrapment is undesirable because bubbles create weak zones and can appear as surface pits once the candy cools. The candy mass then feeds the depositor at the forming wheel. The depositor meters a precise amount into each cavity. Portion volume directly sets lollipop size and weight. Metering is done by piston pumps or gear pumps synchronized to the wheel index. Dose accuracy matters because a low fill yields thin spots and poor stick anchoring, while an overfill creates flash that must be trimmed and increases wrapper puncture risk. The cavity receives the candy dose first or simultaneously with stick insertion depending on machine design. In one approach, the cavity is partially filled, then the stick is inserted, then a second small dose tops off and the cavity closes. In another approach, the cavity closes on a measured candy slug and the stick is driven into it. The common requirement is that candy must be plastic at the moment the stick enters, so the candy wets the stick surface and bonds as it cools. Shaping occurs when the cavity closes. The closing motion forces candy into the spherical geometry and expels trapped air. Venting channels can allow small air pockets to escape so they do not remain as bubbles. Cavity surface finish is polished, so the candy skin releases cleanly. Cavity temperature is managed so candy does not stick or smear. If cavities are too cold, the candy skin sets instantly and can trap air. If cavities are too warm, the candy remains tacky and can deform during demolding. The machine therefore maintains a stable mold temperature through internal circulation. As the formed lollipop exits the cavity, it is still hot enough that the interior is not fully glassy. It immediately enters a cooling system that locks structure. Cooling is staged. The first stage sets the outer surface quickly so the shape stops flowing. This can be done with cool, dry air directed at the candy surfaces. The second stage brings the core temperature down so the entire mass crosses into the glass state. Cooling rate must be controlled because excessive thermal gradients create stress. Stress tends to concentrate around the stick insertion zone because the stick acts as a rigid inclusion and the candy contracts around it. If the outer layer contracts much faster than the inner, microcracks can form. These cracks may be invisible initially, but can propagate during shipping or when humidity changes. Humidity control in cooling is essential. Hard candy absorbs moisture from air. If cooling air is humid, a thin moisture film can form on the warm candy surface. This film dissolves sugar at the surface and then recrystallizes as a rough haze, reducing gloss and increasing stickiness. Cooling tunnels therefore use dry air. Some lines control dew point directly, keeping dew point low enough that condensation cannot form on the candy at any point in the tunnel. Once cooled to handling temperature, lollipops are demolded or released from the forming wheel and transferred to conveyors. Transfer points are designed to avoid impact at the candy head because the surface can still mark if it is too warm. Guides support sticks rather than candy heads because contacting the head can create flat spots. The lollipops pass through inspection and rejection systems. Vision systems can detect off-center sticks, incomplete fill, surface bubbles, and flash around seams. Weight checks can detect underfill and overfill. Reject mechanisms remove defective pieces before wrapping because wrapping a defective piece wastes film and creates downstream jams. Twizzlers are manufactured by converting a cooked sweet base into a plastic, elastic candy dough, shaping that dough continuously through extrusion, setting texture through staged drying and cooling, then cutting and wrapping so the ropes stay chewy and separate without sticking. The most useful place to start is the cutter, because the cutter reveals whether the upstream dough has the right cohesion and whether the rope has been set enough to hold its geometry. If the rope tears at the cut, the dough is underhydrated or too cold. If it smears and strings, the dough is too warm or too wet. The factory therefore tunes the entire process to deliver an extrudate that behaves predictably at the knife. Upstream of the cutter, the rope travels through setting tunnels that control moisture and temperature. Those tunnels are what convert an extruded ribbon into a stable Twizzler's rope with a uniform chew. The rope exits the die warm and pliable, and its interior still contains enough water to make it sticky if packaged immediately. The setting tunnel removes a measured amount of moisture while allowing the matrix to equilibrate so the surface becomes dry enough to handle, yet the core remains chewy. Air temperature, humidity, and velocity are balanced to avoid case hardening. Case hardening creates a tough outer shell and a soft interior, which leads to cracking during bending and an uneven bite. Staged zones, warmer early zones, and gentler later zones reduce that risk. Before the rope ever reaches those tunnels, the line creates the candy dough in a cooker and mixer system designed for high solids. Sugar and glucose syrup are staged as the main carbohydrate system. Granulated sugar is screened to remove clumps and dust because clumps dissolve unevenly and dust can scorch at hot surfaces. Glucose syrup is held in jacketed tanks so viscosity stays stable for metering. Water is filtered and tempered because inlet temperature shifts dissolution and cook stability. Starch and other structure-building solids are held dry and fed accurately because their hydration rate determines dough firmness later. Cooking starts in a dissolver where sugar is hydrated into a clear solution. That solution then moves to a cooker where heat drives off water and raises solids. The cook endpoint is selected so the base becomes plastic when cooled, not glassy like hard candy, and not fluid like syrup. The endpoint is typically controlled by temperature and by flow resistance in the cooker. If the base is undercooked, it carries too much water and produces a sticky rope that never sets. If overcooked, it becomes too stiff, causing high extruder pressure and surface cracking at the die. After cooking, the hot base is cooled into a window where powders can be incorporated without clumping, and flavors can be added without being stripped. At this stage, the line transitions from a boiling syrup process to a dough making process. Structure formers, like starches, must be dispersed and hydrated evenly. Dry starch added directly to hot syrup would form lumps with dry cores. To avoid that, starch can be fed through high shear mixers or introduced as a slurry that is hydrated and cooked separately before blending. The goal is a continuous matrix where starch and sugars form a cohesive network. Acids and salt are staged as low-rate additions. Acid influences flavor and also changes the behavior of the carbohydrate matrix over time by shifting inversion and hygroscopicity. For that reason, acids are added after the hottest zones and mixed thoroughly but gently. Flavor and color are also added late. Flavor injection is done downstream of intense heat to preserve volatile components. Color is metered as a concentrated solution to avoid adding excess water. Once all components are combined, the mass enters intensive mixing. This is where it becomes a uniform plastic dough. The mixer uses high torque elements that fold and shear. Shear must be sufficient to eliminate streaks and fully wet powders. Shear must not be so aggressive that it whips air into the dough, because trapped air causes bubbles and weak spots in the extruded rope. Mixing endpoint is judged by uniform color, uniform torque, and a stable temperature. Temperature is monitored continuously because the dough must remain plastic but not overly soft. The dough then enters a conditioning stage before extrusion. Conditioning equalizes moisture throughout the mass and stabilizes temperature so extrusion pressure does not pulse. This can be done in a holding hopper with gentle agitation or in a screw conveyor that provides a fixed residence time. The objective is to deliver the extruder a steady feed that produces a steady rope diameter. Extrusion is the primary shaping method. The dough is fed into a screw extruder whose barrel is temperature controlled. The screw compresses and pushes the dough forward. Compression removes minor voids and increases cohesion. Barrel temperature keeps the dough in the plastic range. If the barrel is too cool, pressure rises and the rope surface becomes rough. If too warm, the rope surface becomes tacky and can collapse after exiting the die. The die defines rope, cross-section. Twizzlers ropes are typically round or slightly shaped, depending on the product format. Die temperature is controlled because cold dies cause surface tearing and hot dies cause smear. Pressure at the die is monitored. It acts as an indicator of dough viscosity and hydration. Stable pressure produces stable diameter, which matters because diameter controls final chew and package weight. Immediately after extrusion, the rope is guided by takeoff belts. Belt speed must match extruder output to avoid stretching. Stretching thins the rope and aligns the matrix, which can make the bite tougher and can produce uneven twist definition. The rope is supported so it does not sag, because sag introduces diameter variation and can cause twists to tighten unevenly. Twist formation, when used, is produced by controlled rotation relative to forward motion. A twisting head grips the rope or imparts rotation while the takeoff belt pulls. The twist pitch is set by the ratio of rotational speed to linear speed. A tighter pitch yields a more pronounced twist and slightly denser bite. A looser pitch yields a smoother rope and a softer feel. Twist must be consistent along the rope, because variation creates weak points where the rope can split during cutting or packaging. After twisting, the rope enters the staged drying and cooling tunnels described at the beginning. These tunnels are engineered to hit a final moisture endpoint that supports chew without stickiness. Early tunnel zones focus on removing surface moisture so the rope can be handled without clumping. Later zones allow moisture to migrate from the core to the surface gradually and leave the rope at a stable water activity. Airflow is controlled to avoid whipping ropes into each other, and the rope is kept separated by lane guides. Once the rope reaches the target set, it passes to cutting. Cutting uses rotary blades, or guillotine cutters, synchronized to belt speed. Synchronization controls piece length and therefore piece weight. Blade sharpness is managed because a dull blade drags and creates strings at the ends. Stringing is a sign that the rope is still too warm or too wet. A clean cut indicates the surface has set and the interior has enough cohesion to fracture neatly at the blade. Cut pieces then go through a short post-set stage. This allows freshly cut ends to dry slightly so pieces do not stick end to end. It also allows any residual heat from cutting friction to dissipate. If a light surface treatment is used to improve flow, it is applied here. A tiny amount of neutral oil can be misted while pieces tumble gently. The oil film reduces surface friction and helps prevent sticking in the wrapper. Oil application is minimal because excess oil changes mouthfeel and attracts dust. Screening can follow to remove fragments created during cutting and conveying. Removing fragments improves pack appearance and reduces dust that can interfere with seals. Metal detection or other final integrity checks can be positioned here because product flow is stable and pieces are separated. Wrapping begins with controlled feeding into flow wrappers. Pieces are aligned into lanes and spaced, so each wrapper cycle receives one piece. Film is formed around the rope and sealed with heat and pressure. Seal dwell and temperature are tuned, so seals are strong without overheating the candy surface, because overheating can soften the rope and deform it under film tension. Film tension is controlled so it sits snug without squeezing the rope flat. Slush. Puppy-style slush is manufactured by producing a shelf-stable flavored concentrate, then engineering a dispensing system that freezes a diluted beverage into a suspension of tiny ice crystals without forming a solid block, then keeping those crystals moving so the product stays scoopable and uniform in a cup. The easiest way to understand the production chain is to start at the point of consumption, the slush machine. A slush machine is essentially a controlled, scraped surface freezer that must keep a mixture right at its freezing curve. It needs enough sugar and solutes to depress the freezing point, enough viscosity to keep ice crystals suspended, and enough agitation to prevent large crystals from growing. Everything that happens in the factory is designed to make a concentrate that, when diluted, behaves correctly inside that machine. The slush machine relies on a mix ratio that is tightly defined. The concentrate is not used full strength. It is diluted with water to a target sugar concentration. If the mix is too weak, freezing point rises and the machine produces a hard ice mass or large crystals that separate into watery and icy zones. If the mix is too strong, freezing point drops too far and the machine struggles to freeze enough, yielding a cold syrup rather than slush. That is why the factory builds the concentrate with a known soluble solids level and a known acidity, and why it specifies a dilution ratio. Concentrate manufacturing begins with water handling and sweetener preparation. Water is filtered to remove suspended solids because solids can seed haze and clog dosing valves. The main sweetener can be sugar syrup, glucose syrup, or a blend. For sugar-based concentrates, granulated sugar is dissolved in heated tanks with agitation until the solution becomes clear. Density is monitored because it defines sweetness and freezing behavior after dilution. For syrup-based sweeteners, the syrup is held warm so viscosity is stable, and metering is accurate. Acidity is set next because pH affects flavor perception and stability. Acid is prepared as a liquid solution for accurate dosing, and then injected into the blending tank. pH is measured and adjusted to a narrow set point. A stable pH also helps preserve certain flavor components. Color is handled as a separate dosing stream. It is stored in tanks with gentle mixing and filtered before dosing so it remains uniform. Flavor is prepared as a concentrate that can be dispersed reliably in water. Many slush flavors contain both water-soluble aroma components and oil-based notes. Oil-based components are emulsified, so they do not separate in the finished concentrate. Emulsification is done with high shear mixers that reduce droplet size. Droplet size matters because large droplets separate and ring at the surface, while small droplets remain stable and deliver consistent aroma. The finished flavor concentrate is filtered to remove particulate and then metered into the main blending tank. Viscosity modifiers can be included in small amounts to influence mouthfeel and crystal suspension. These components must be fully hydrated and dispersed, so they are added under controlled shear and allowed to mix until uniform. The goal is not a thick beverage, but a mix that can hold microcrystals evenly during dispensing and drinking. Once sweetener, acid, color, flavor, and any stabilizers are in the blending tank, the concentrate is mixed to uniformity without entraining air. Air entrainment can cause foaming in packaging and can affect how the concentrate mixes with water later. The concentrate is then filtered to remove any remaining undissolved particles that could settle or clog dispensing systems at retail. Quality checks on the concentrate focus on soluble solids, pH, color density, and flavor strength. Soluble solids are measured to ensure the dilution ratio will yield the intended freezing point depression. pH is checked for consistency because it affects taste and stability. Color is checked because it must remain stable in storage and consistent from batch to batch. The concentrate then moves to packaging. Packaging is designed for high sugar liquids. Concentrate is filled into jugs, bottles, or bag-in-box systems. Bag-in-box is common because it minimizes oxygen exposure and allows easy dispensing at retail. Filling uses metered valves and is controlled to avoid splashing and foaming. Caps or fitments are applied immediately. Seals are checked because leaks allow contamination and sugar crystallization around closures. Finished packages are coated and cased. At retail, the concentrate is mixed with water to the specified ratio. That mixing can be done in a separate tank or directly in the machine reservoir. The purpose is to produce a ready mix with the correct sugar concentration and acidity. The water used at retail can vary. So many systems specify filtration and cold water use to reduce variability. Inside the slush machine, freezing is achieved by a refrigerated cylinder and a rotating scraper. The cylinder wall is cooled below the freezing point of the mix. A thin layer of ice forms on the cold wall. The scraper continuously removes that ice layer and breaks it into small crystals that are pushed into the bulk liquid. Continuous scraping prevents the ice from building into a solid sheet that would block heat transfer. The rotating mechanism also keeps the entire mixture moving so ice crystals remain suspended rather than settling. The formation of microcrystals is controlled by the freezing point depression of the mix. Sugar and dissolved solids lower the freezing point so the mixture does not freeze solid at typical machine temperatures. Instead, a fraction of the water freezes as ice, while the remaining liquid becomes more concentrated. This concentrated liquid phase acts as a lubricating syrup between ice crystals. The machine aims for a steady balance where ice fraction stays in a target range. Agitation speed is a key control. If agitation is too slow, ice crystals grow larger and the product becomes coarse and icy. If agitation is too fast, the mixture can incorporate air and become foamy, and frictional heat can reduce freezing efficiency. The scraper geometry and clearance are engineered to remove ice efficiently without creating excessive shear that would heat the mixture. The machine also relies on viscosity to prevent separation. If the liquid phase is too thin, ice crystals can settle and form a dense, icy bottom layer, while the top becomes watery. A slightly more viscous liquid phase helps keep crystals evenly distributed. This is why concentrates often include small amounts of stabilizer and why the soluble solids level is strictly maintained. Temperature control in the machine is staged through a thermostat system that cycles refrigeration. The goal is not a constant deep freeze, but a controlled temperature near the mix's freezing curve. If the machine overcools, ice fraction rises too high, and the product becomes stiff and difficult to dispense. If it undercools, ice fraction drops, and the product becomes slushy syrup. Machines often use sensors that monitor torque on the agitator as an indirect measure of slush stiffness, adjusting cooling accordingly. From a factory perspective, this machine behavior drives the formulation targets. The concentrate must produce a ready mix with a predictable freezing curve. That means controlling sugar type and concentration. Different sugars and syrups depress freezing point differently and change viscosity. The factory chooses a sweetener system that creates the desired crystal fraction at typical machine temperatures. Acidity and flavor intensity are also tuned with the machine in mind. Cold temperatures reduce flavor perception. Therefore, the ready mix is formulated with enough flavor concentration to remain noticeable when frozen. Acidity can provide brightness that cuts through cold dullness. However, acidity also affects the stability of certain emulsions and can influence syrup behavior over time. The factory balances these factors. Color stability is another practical requirement. Slush is displayed in clear machine bowls and must remain visually uniform. Colorants must remain stable under light exposure and cold temperatures. The factory filters concentrate to remove particles that would settle and create gradient bands.